Hello there, and welcome to Science for Sleep, a small, quiet place where curiosity slows down enough for us to look at it closely and let it settle. Tonight, you and I are drifting into one of the most bewildering truths we've ever discovered about the cosmos, something so enormous and so persistent that it touches everything from distant galaxies to the space between the atoms in your own body. It's the realization that the universe is not just expanding, but doing so faster as time passes. A strange, steady acceleration that no one expected and no one fully understands. The kind of mystery that doesn't rush to reveal itself, but lingers in the background of the night sky, quietly reshaping our sense of reality. Before we move too far into that idea, take a moment with me to notice where you are right now. Maybe you're lying down with the lights low, or sitting softly in a quiet room at the end of a long day. Maybe you've got headphones on and the world around you has faded into a gentle hush. Wherever you are, it's only you and this slow unravelling of a cosmic puzzle, and I'd love to know, if you feel comfortable sharing, where in the world you're listening from tonight. I'm always curious about the quiet corners people settle into when they press play on something meant to help them unwind. What does the sky look like where you are? Is it bright with city lights or dark enough that you can see a few stars? If you find this kind of calm exploration comforting, or if the gentle flow of ideas keeps you company while you settle in for the night, I'd be grateful if you gave the video a like or subscribed. It helps this quiet little space reach others who might also enjoy learning something soothing at the edge of sleep. But there's no pressure at all. Just an invitation to stay connected if you want these peaceful wanderings to find their way to you more often. Now let's take a soft step into the idea at the centre of our time together. The fact that the universe is expanding at all is interesting enough. It means the galaxies are drifting away from each other, the distances between clusters of stars are stretching, and the fabric of space itself is slowly widening. But the real surprise, the one scientists stumbled upon with a mix of confusion and disbelief, is that this expansion is speeding up. Not drifting lazily, not slowing down like something losing momentum, but steadily accelerating as though some unseen influence is nudging everything outward with a little more strength over longer stretches of time. It's a curious thing to sit with, because the universe doesn't seem like something that should behave this way. Most familiar things slow down if nothing keeps pushing them forward. A ball rolls to a stop, a swing loses energy, a tossed object arcs and falls. Our everyday experiences don't include anything that naturally speeds up while spreading apart, so when astronomers first noticed the signs of acceleration, it didn't line up with what we expect from normal motion, and even now, decades later, we still don't know what's causing it. We've given the unknown influence a name, dark energy, but naming a mystery doesn't solve it. It only gives us a way to refer to something we're still trying to understand. To get comfortable with this idea, imagine watching a cluster of glowing lanterns drifting apart on a still lake. At first, they move away from each other at a steady pace. You'd expect that if nothing else touches them, they might keep drifting or slow slightly as the motion evens out. But imagine instead that the lanterns begin gliding apart faster and faster as time goes on, with no visible force at the surface of the water explaining why. It would make you question the lake itself, the way it behaves, and whether something underneath is affecting the lanterns in a way you can't see directly. That's a bit like the puzzle of the accelerating universe. The lanterns are galaxies, the lake is space-time, and whatever's causing the acceleration is hidden beneath the surface. But unlike a lake, space-time isn't something we can skim our hand across or stand beside. We only infer its behaviour by watching what happens to distant objects, and since the universe is unimaginably vast, many of the clues arrive slowly, stretched out across billions of light years. Each faint signal from a distant star or galaxy carries with it a quiet message about the way the universe behaved long before Earth even existed. When those signals show that galaxies farther away are moving faster than galaxies closer to us, it hints that the expansion wasn't always the same. Something changed. Something began pushing harder. The discovery didn't arrive all at once or with dramatic fanfare. It came in the form of measurements, graphs, and subtle patterns of light. Scientists studying distant supernovae noticed that the light reaching us was dimmer than expected. Not because the stars themselves were unusually faint, but because they were farther away than predicted based on how fast the universe should have been expanding according to earlier theories. Those measurements implied a surprising conclusion. The expansion must have been getting faster over time, stretching the distance more than anyone anticipated. It's strange to think about these things in the quiet hours of the night. The idea that while you're listening, the universe continues widening at an accelerating pace, even in this very moment. Galaxies drift a little farther, clusters shift apart. The space between everything expands at an almost imperceptible rate. It's not something we feel or see or sense in any personal way. Your room doesn't stretch. Your chair stays the same size. At human scales, the effect is so tiny that it has no influence on your everyday life. Yet when you look across distances measured in billions of light years, the change becomes impossible to ignore. The scale of the cosmos amplifies subtle things into grand ones. Near the beginning of our universe, everything was much closer together. Matter clumped, stars ignited, galaxies formed and collided, sculpting the structures we see now. Gravity was the dominant force shaping these early moments, pulling things inward, forming clusters, gathering dust into stars. With so much matter packed together, it would be natural to assume that gravity should slow expansion down over time. In fact, that was the expectation for many decades. The universe may expand for a while, the thinking went, but eventually gravity might slow it, maybe even pull it back inward, depending on how much matter existed. The idea of the universe speeding up was so far from the expected path that it took careful, repeated observations to convince people it was happening. And yet the evidence grew. More supernovae were studied, more distant galaxies were measured, more light curves matched the same unusual pattern. The acceleration wasn't a mistake or an illusion, it was a feature of the cosmos itself. So here we are, living in a universe that doesn't simply expand but does so at an increasing rate, driven by something that has no direct detection, no clear explanation, and no easy analogy. Dark energy isn't something we can point to or observe directly. It's inferred from the behavior of space, a kind of placeholder for an unmeasured cause. It's the name we give to an unknown that pushes everything outward. As we move deeper into this topic, we'll take things slowly, one idea at a time, because the story of the accelerating universe is not something that demands urgency. It's a broad, steady stream of discoveries and theories that can be explored in a relaxed way. We'll look at how the expansion first came to be noticed. We'll examine what redshift tells us about the movement of galaxies. We'll explore why the acceleration surprised scientists, what dark energy might be, and how its presence affects the future of the cosmos. And through all of that, we'll continue to keep the pace soft and unhurried, letting each thought stretch into the next without collapse or rush. For now, it's enough to rest in the opening idea. The universe is expanding faster over time, quietly, steadily, without any sign of slowing. A silent widening that shapes everything from the distribution of galaxies to the ultimate fate of all structures in existence. And as we follow the story further, we'll see how this simple observation leads to deeper questions about what the universe is made of, how it began, and what it might become far into the future. When you first hear that the universe is expanding, it might seem like an interesting but distant fact, the sort of thing that sounds impressive but doesn't quite connect to anything you experience in your daily life. Then you learn that not only is it expanding, but it's doing so faster as the years pass, and suddenly the idea becomes far more puzzling. A universe that expands is one thing. A universe that speeds up while doing it is something else entirely. It introduces a small knot of curiosity. Why would everything drift apart in a way that accelerates instead of slows? Why would the expansion grow stronger rather than weaker? That question sits quietly at the centre of some of the most important discoveries in modern astronomy, and it's where our journey continues. To get a sense of why this mystery matters, it helps to picture the universe not as a static scene, but as something that has been changing steadily since its earliest moments. In the time after the Big Bang, everything was packed together much more tightly than it is now. Galaxies hadn't formed yet. Stars hadn't ignited. Space was hot, dense, and expanding rapidly. As it stretched and cooled, the matter within it began to clump together under the pull of gravity. Over millions of years, regions of slightly higher density became nurseries for the first stars. Clouds of gas, drawn together by their own mass, ignited into the earliest points of light. From there, galaxies began forming, merging, and shaping the cosmic structures we see today. That early stage sets up an expectation. If all the matter in the universe pulls on all the other matter through gravity, then the expansion should gradually slow down. The gravitational attraction between galaxies should act like a gentle brake. Not enough to pull everything inward again unless there was huge amounts of mass, but enough to reduce the rate at which galaxies drift apart. For a long time that was the assumption. It seemed reasonable based on everything we knew. Gravity pulls things together. The universe expands outward. The two effects should work against each other, and over time the outward motion should slow. But the universe didn't agree. Instead of slowing, it began doing something unexpected. It started expanding faster, and not just slightly faster. The acceleration was clear, steady, and measurable, a kind of widening that revealed itself in the way light from distant objects reached us. The first hints of this came from studies of distant supernovae. These brilliant explosions, which mark the end of a massive star's life, act as useful beacons. Because they release a predictable amount of light, astronomers can measure how bright they appear to us and determine how far away they are. When two different groups of researchers studied these supernovae in the late 1990s, they found something unusual. The light was dimmer than expected. That meant the stars were farther away than anyone predicted based on a universe that was slowing its expansion. The only explanation that made sense was that the expansion had been speeding up for billions of years. This wasn't something people were looking for. The goal was to measure the slowing. Instead, they found the opposite. The data pointed toward a universe that had been accelerating for a long time. It wasn't a small adjustment. It was a major shift in our understanding of how the cosmos behaves. The idea that the universe could speed up didn't match what gravity alone would allow. Gravity always pulls. If the only major influence were mass, then the expansion would slow, but it wasn't slowing. Something else had to be happening. This something else is what we refer to as dark energy. Not because we know what it is, but because we don't. The name is a placeholder that acknowledges the unknown nature of whatever is causing the acceleration. It isn't ordinary matter. It isn't dark matter. It isn't radiation. It seems to be something woven into the structure of space itself, something that doesn't thin out as the universe expands, something that keeps applying the same push no matter how much space stretches. When people first hear the term dark energy, they sometimes imagine it as a kind of substance filling the universe. But that's not quite what the idea suggests. It's more accurate to think of it as a property of space rather than something floating in it. Space isn't empty in the way an untouched vacuum seems. Even the emptiest regions contain fields and fluctuations that have effects we don't fully understand. Dark energy might be tied to these deeper properties. It could be something built into the very geometry of the cosmos. The strange part is that the more space there is, the more of this unknown influence exists. And since the universe keeps expanding, there's more and more space over time. If dark energy remains constant in its density, then the total amount of it grows as the universe grows. That means the accelerating push becomes more influential the larger the universe becomes. In earlier times, when matter was packed more closely together, gravity had a stronger effect relative to this mysterious influence. As everything spread out, gravity weakened, and dark energy began to dominate, slowly making the expansion speed up. This picture creates a different way of thinking about the universe. Instead of imagining everything drifting apart in a way that should naturally decelerate, we have a cosmos in which the expansion pushes itself forward more aggressively as time goes on. It isn't a runaway effect, but it is steady, measurable, and consistent with observations. And it raises a simple but profound question. Why is the universe built this way? Before the acceleration was discovered, many scientists considered the possibility that the universe might one day slow enough to stop expanding entirely. There were models where the expansion could halt and reverse, causing everything to collapse inward in a distant future. Others suggested the expansion might continue forever, but at a decreasing rate. The discovery of acceleration made both ideas unlikely. Instead, it pointed toward a universe that becomes more stretched, more spacious, and more diffuse over time. Not in a sudden or dramatic way, but slowly, steadily, almost quietly. It's interesting to think about the way such a discovery changes the way people imagine the future of the cosmos. Instead of a universe that might one day pull itself back together, or even coast in a stable way, we see a universe that drifts further apart in an accelerating manner. Galaxies that are already far from each other will become more distant. Clusters that are gravitationally bound will stay together, but anything not held by gravity will eventually slip beyond our reach. The night sky that looks so full to us now may gradually empty over unimaginably long timescales, not because stars vanish, but because the space between everything grows so wide that light may never bridge the gap. And yet, even with this quiet but powerful acceleration occurring all around us, nothing about your immediate surroundings changes. The expansion only affects distances on very large scales. Within galaxies, gravity is strong enough to keep stars bound. Within solar systems, gravitational attraction easily overwhelms the influence of dark energy. Even at the scale of galaxy clusters, the structures remain held together. So while the universe expands faster, your home, your world, and your experience remain unchanged by this effect. It's something that plays out on scales so large and over time so long that we don't sense it directly. We only know about it because of the faint light that reaches us from far beyond our own galaxy. Thinking about this slow widening brings up another interesting question. If the universe is accelerating now, was it always doing so? The answer appears to be no. In the early universe, matter and radiation were far more influential than dark energy. They pulled together strongly, shaping the formation of stars and galaxies. The acceleration only began once the universe had expanded enough that the matter was sufficiently spread out. Before that, gravity dominated. Later, dark energy took over. This shift from deceleration to acceleration marks a turning point in cosmic history, though it unfolded so gradually and over such long spans of time that nothing dramatic happened at any particular moment. There was no sudden change in the night sky, no visible sign. The universe simply eased into a new mode of expansion. It's also interesting to reflect on how all of this depends on the way we interpret observations. When astronomers study the universe, they can't watch galaxies move in real time. Everything is too far, the motion is too slow. Instead, they rely on light that has been travelling for billions of years. That means they see galaxies as they were long ago. A distant supernova might show us how the universe behaved 6 billion years in the past. Another might show conditions from 9 billion years ago. By comparing many of these distant sources, scientists piece together a timeline. They can tell when the universe's expansion slowed and when it began to speed up. The quiet part of this mystery is that all of these conclusions come from tiny differences in brightness, from small shifts in the wavelengths of light, from measurements that require great care and patience. There's nothing loud or dramatic about the signals themselves. They're faint, distant, and subtle. And yet, from these faint clues, the entire story of cosmic acceleration emerges. You might wonder why this expansion, even if accelerating, should matter to us. After all, if it doesn't affect the scale of planets, stars, or everyday life, What does it change for anyone here? The answer lies in the way it shapes our understanding of the universe. When something as fundamental as expansion behaves differently than expected, it suggests that there are aspects of reality we haven't yet understood. Dark energy, whatever it turns out to be, might reveal a new part of physics. It might connect to quantum fields or something we haven't imagined yet, and the acceleration of the universe may be telling us that space itself has properties we don't fully grasp. This realization changes the way we think about fundamental questions. What is space? What does nothingness truly contain? How do the forces of nature work together on the larger scales? The accelerating universe touches all of these questions. It's not only an observation about how galaxies move, it's a sign that the underlying structure of reality has layers we haven't peeled back yet. In a way, the mystery isn't loud or urgent. It's a slow puzzle, one that scientists have been working on for decades and will likely continue exploring far into the future. Every new measurement adds a piece. Every new model offers a possible explanation. Yet the core of the mystery remains. Something is causing the universe to accelerate. Something is counteracting gravity on the larger scales. Something is influencing the entire cosmos at once. Long before anyone suspected that the universe was stretching, long before telescopes were powerful enough to detect distant galaxies, people assumed the night sky was fixed. The bright points of light overhead seemed steady and unchanging. Even the slow motions of planets could be followed by patient observers, but the stars themselves appeared anchored. Their patterns repeated year after year. Nothing about them suggested that the cosmos was in motion at all, let alone drifting outward. For most of human history, the idea that stars could be moving away from us would have sounded strange, unnecessary, or even impossible. The first hints that the universe might not be as still as it appeared arrived quietly. No one made the discovery in a single moment. Instead, it came through patient observation, new technology, and the gradual development of ideas that built on each other. To understand how we first noticed the stars drifting apart, it helps to take a slow walk through the experiences of the early astronomers who were trying to measure the cosmos at a time when the tools were still crude and the distances involved were almost beyond imagination. One of the earliest clues came from something known as stellar parallax, a small shift in a star's apparent position as the Earth moves around the Sun. It was tiny, almost too small to detect with the tools available at the time. Many astronomers believed that the stars were so far away that any shift in their positions would be invisible, and for centuries that appeared to be true. When parallax was finally measured in the 1800s, it became clear that the stars were not part of a fixed dome but incredibly distant objects. The universe was much larger than anyone expected. That idea alone hinted that the sky was not the simple, unchanging backdrop it seemed. As telescopes improved, astronomers noticed that some stars appeared redder or bluer than expected. The differences were subtle and difficult to interpret at first. It took time for people to realize these shifts in color weren't caused by the stars themselves, but by their motion. A star moving away from us stretches its light slightly, shifting it toward the red part of the spectrum. A star moving toward us compresses its light, shifting it toward the blue. This effect is called the Doppler shift, and it applies to sound as well as light. If you've ever listened to a train whistle lower in pitch as it moves away, you've already experienced something similar. When astronomers applied this principle to the light from stars and later from galaxies, they realized that many of them showed a redshift, meaning they were moving away from us. At first, this was surprising but not alarming. People knew that objects in space could move in various directions. A star drifting away didn't immediately imply anything about the universe as a whole. It was simply another motion among many. But then came the discovery of galaxies beyond our own. For a long time, the spiral shapes observed in telescopes were thought to be nebulae within the Milky Way. Only in the 1920s did Edwin Hubble, using the powerful telescopes at Mount Wilson Observatory, realize that these spirals were entire galaxies. each filled with billions of stars. This changed everything. If these objects were outside our galaxy, then the universe was far vaster than anyone had imagined. Hubble measured the distances to these galaxies using a special type of star called a Cepheid variable. These stars brighten and dim in a way that reveals their true brightness. By comparing how bright they appear from Earth, astronomers can determine how far away they are. It's a technique that becomes a sort of cosmic measuring stick, allowing distances to be calculated across vast stretches of space. Once Hubble had reliable distances, another pattern began to emerge. The farther away a galaxy was, the more its light was redshifted. Not just a little more. The relationship was striking. Distant galaxies were moving away faster than nearby ones. Everything was drifting apart in a way that suggested a pattern rather than random motion. This was the first clear sign that the universe itself might be expanding. Space wasn't just containing the galaxies, it seemed to be stretching, carrying them along like dots on the surface of an inflating balloon. This idea didn't immediately settle comfortably into the scientific community. The notion that the universe was expanding wasn't widely accepted at first. Many astronomers preferred the idea of a steady, unchanging cosmos. A universe in motion felt unstable, like something grand and orderly was giving way to something unpredictable. Hubble's results, however, were difficult to ignore. The redshifts were consistent. The distances matched the speeds. The pattern kept repeating. The simplest explanation was that space was expanding. There's a useful way to understand why these drifting galaxies pointed toward expansion. Imagine you have a long elastic band with tiny beads glued onto it. If you stretch the band gently, every bead moves away from every other bead. The ones farther from your fingers move more than the ones close by, simply because there's more elastic between them. If you placed observers on these beads, each one would believe the others were moving away, and might even conclude that they themselves were at the centre of the stretching. But the truth wouldn't be about any one bead. It would be about the elastic band itself. The galaxies behave much like those beads. None of them is at the centre. All of them see the others drifting away, and the more distant a galaxy is, the faster it appears to recede because more expanding space lies between. It took time for this interpretation to gain acceptance. Many scientists attempted alternative explanations. Some suggested the redshift could be caused by light losing energy during its journey across the cosmos. Others proposed that galaxies might be moving through space in a coordinated way. But these ideas didn't fit the data as well as the expansion model. The distances and velocities aligned too neatly with the idea of a stretching universe. As more measurements accumulated, confidence grew. Galaxies all across the sky showed the same pattern. No region behaved differently. There was no preferred direction, no sign that the motion was caused by anything within the Milky Way. Everything pointed toward a universal phenomenon affecting space at large. Once astronomers accepted expansion, they began tracing it backward in time. If the universe was larger today than it was in the past, then there must have been a time when everything was closer together. This idea eventually led to the concept of the Big Bang, a period when the universe was far more compact, dense and energetic than it is today. The redshifts weren't just signs of stars drifting away. They were evidence of the universe's entire history unfolding. But the story didn't end there. As scientists studied the redshifts of more distant galaxies, they expected to find signs that the expansion was slowing. Gravity, after all, pulls things together. Over billions of years, it should have acted like a brake, reducing the expansion rate. This seemed logical based on our understanding of forces and motion. What researchers found instead was something unexpected. Some of the farthest galaxies, whose light had been travelling toward us for billions of years, showed signs that the expansion was slower in the distant past. That meant the expansion had sped up since then. The universe wasn't drifting apart in a simple, steady way. It was accelerating. This discovery added a new layer of complexity to an already puzzling story. To appreciate the surprise, imagine watching a rowboat drift across a lake. At first, it slows gently as the momentum fades. But then, without warning, it begins speeding up as though caught by a current. If you can't see the current, you're left searching for something that could explain the sudden increase in speed. That's similar to what astronomers faced with cosmic acceleration. They saw the behaviour clearly but lacked a straightforward explanation. This puzzle led to new lines of investigation. Scientists revisited old measurements, looked for errors, and checked for alternative possibilities. But the results held steady. The acceleration was real. And so the idea of dark energy entered the scene, not as a complete solution but as a necessary placeholder. Something was pushing the universe outward. Something was counteracting gravity on the larger scales. Something was influencing everything at once. This journey from noticing slight colour shifts in starlight to uncovering the accelerating expansion of the cosmos shows how gradual and intricate scientific discovery can be. It wasn't one person making a dramatic announcement. It was generations of careful observations, improvements in technology, and a willingness to consider the possibility that the universe might behave differently from what intuition suggests. Through all of this, the drifting of galaxies became a key piece of evidence. The redshifts weren't just subtle colour variations, they were messages from the cosmos, hints about the structure of reality. The galaxies weren't moving through space in the usual sense. Space itself was stretching, carrying them along. It's interesting to reflect on how this understanding changes the way we think about our place in the universe. Instead of imagining ourselves in a fixed, static environment, we begin to see ourselves as part of a dynamic, evolving cosmos. The night sky becomes less of a backdrop and more of a living record of motion, history, and change. Even though the stars look motionless to the eye, their light tells a different story. The universe is not fixed. It never was. The distant galaxies drift away slowly, steadily, following a pattern that stems from the nature of space itself. These discoveries also highlight how much of what we know relies on interpreting faint signals. A small shift in a star's colour, measured with great care, can reveal motion across unimaginable distances. A dimmer than expected supernova can indicate that the universe has changed its behaviour over billions of years. Tiny things add up to large insights. Knowing that galaxies drift apart helps us understand why the universe looks the way it does. It also sets the stage for deeper questions. What is dark energy? How does it shape the future of the cosmos? What does it tell us about the fabric of space-time? When people first hear the word redshift, it can sound like a technical term meant for astronomy textbooks, rather than something connected to the gentle flow of ideas you might settle into at the end of a long day. But redshift is actually one of the simplest and most useful clues we have for understanding how the universe behaves. It explains how we know that distant galaxies are drifting away. It describes how the stretching of space affects the light that travels through it, and it quietly bridges the gap between what we can see in the night sky and the much larger story unfolding across billions of light years. To begin making sense of it, all you need is the idea that light behaves like a wave. Even though it doesn't feel like a wave when it touches your eyes, it has crests and troughs, much like ripples on water. The distance between these crests determines whether light appears blue, red, or somewhere in between. Shorter wavelengths appear more blue. Longer wavelengths appear more red. This property lets astronomers treat light as a messenger, carrying information about the source that produced it and the space it has travelled through. The same way a sound shifts when its source moves, light shifts when the object emitting it moves relative to you. If something moves toward you, the waves get slightly compressed, pushing them toward the blue end of the spectrum. If something moves away, the waves stretch, shifting the light toward red. This is the Doppler effect, and you experience a version of it every time a vehicle passes by with its pitch lowering as it moves away. Light doesn't make sound, but the principle is similar enough that the analogy helps. When astronomers examined the light from distant galaxies, they found that the wavelengths were stretched toward the red end of the spectrum. This meant the galaxies were moving away from us. At first, this seemed like an interesting observation, but not necessarily a sign of anything universal. After all, objects in space can move for many reasons. But as more measurements accumulated, a pattern appeared. Galaxies in every direction, near and far, all showed redshifts, and not only that, but the farther away a galaxy was, the more its light was stretched. This wasn't random drift. It was a consistent relationship that suggested something much larger was going on. This is where the idea of cosmic stretching enters the picture. Instead of imagining galaxies flying through space like projectiles, it's more accurate to think of space itself expanding. When the space between two galaxies stretches, the galaxies move apart without either one needing to propel itself. The galaxies simply follow the changing geometry around them, and because light travels through that same space, its wavelength stretches along with it. That stretching is what creates the redshift we observe. To understand why this stretching leads to a stronger redshift for more distant galaxies, imagine drawing dots on a long rubber strip. If you gently pull on the strip, every dot moves away from every other dot. The ones farther apart experience a greater overall stretching, so the relative motion appears larger at greater distances. If you were standing on one dot, you would see every other dot moving away, and the ones farther from you would seem to move faster. This is the same pattern astronomers discovered when measuring galaxy redshifts. Redshift is useful because it provides a direct way to measure distance and motion in the universe. The more stretched the light is, the farther away its source likely lies and the faster it is moving away from us. These measurements made it possible to build a map of the cosmos that shows not only where things are, but how they are moving within the fabric of space. The patterns aren't arbitrary, they reflect the expansion of the universe itself. The concept becomes even more interesting when you realize that redshift isn't only caused by motion. In an expanding universe, even a stationary galaxy will show redshift if the space between us expands while the light is traveling. This is sometimes called cosmological redshift, and it doesn't rely on the galaxy moving through space. It depends entirely on how space behaves while the light crosses it. This makes redshift a powerful tool for studying the large-scale structure of the universe, something far beyond human perception, and yet accessible through the quiet patterns of starlight. There's a small detail here that's worth lingering on for a moment. The light we see from a distant galaxy might be billions of years old. When that light left its source, the universe was different. Galaxies were closer together. Dark energy, whatever it turns out to be, hadn't yet made the expansion accelerate as strongly as it does now. The light then spent billions of years travelling through space that kept stretching. By the time it reaches Earth, its wavelength has been pulled longer by the cumulative effect of this expansion. That long journey gives us a glimpse into the past. Each redshift measurement is like opening a small window into a different era of the universe. Because of this, redshift is not just a measurement of motion, it's a record of time. The greater the redshift, the farther back into cosmic history we are looking. A nearby galaxy might show only a small redshift, meaning the light left fairly recently, and the space it travelled through didn't stretch very much. But a very distant galaxy could show a large redshift, indicating that its light began its journey long ago, and that the universe has expanded significantly since then. One of the reasons redshift is such a valuable part of astronomy is that it allows us to create a timeline of cosmic events. By examining the redshifts of galaxies at various distances, scientists can reconstruct how fast the universe was expanding at different stages. This is how researchers first discovered that the expansion is accelerating. By comparing distant supernovae, which show the universe's behaviour billions of years ago, with closer ones that tell us how it behaves now, they found that the expansion rate has changed. Redshift was the tool that revealed this shift. Another important element in this story is the idea that redshift increases not only with distance, but also with the amount of time the light has spent travelling through expanding space. This gives rise to what's called the Hubble-Lemaitre law. It describes how the velocity of a galaxy's recession is proportional to its distance from us. Even though the galaxies themselves aren't pushing outward with engines or rockets, the space between them increases at a steady rate, making it seem as though they are rushing away. The law originally appeared as a straight line on a graph plotting velocities against distances. The farther away a galaxy was, the greater its apparent velocity. This was not a coincidence. It was a sign of uniform expansion. Nothing in the graph singled out a specific center. Instead, it implied that expansion looks the same from every location. Any observer in any galaxy would see the same pattern. This idea can feel counterintuitive at first, but it becomes clearer when you consider that expansion affects all of space equally. This doesn't mean the universe expands at the same rate everywhere. Local areas bound by gravity, like galaxies or clusters, don't grow. The pull of gravity within them is strong enough to resist the expansion. But on large enough scales, beyond the reach of gravitational binding, the stretching of space becomes noticeable. It quietly carries galaxies away from one another without disrupting the structures that remain held by gravitational attraction. It can be helpful to pause and really picture this difference. Your home, your planet, and your solar system aren't affected by cosmic expansion because their structure is stable. Gravity dominates at those scales. But between galaxies, where distances are enormous and gravitational connections are weak, the expansion becomes the dominant influence. The redshift of distant starlight is the signature of that influence. Sometimes people wonder why the universe expands at all, or why redshift should be tied to expansion instead of simple motion. The answer lies in the uniformity of the observations. If galaxies were simply moving away through space, we might expect to see some patterns or directional biases, but the redshifts are uniform across the sky, suggesting that the motion is not individual but collective. Every direction shows the same behaviour. That consistency is best explained by expansion, not by galaxies having unusual or coordinated motions. Another useful way to understand cosmic stretching is to think about the difference between objects moving through space and space itself changing. If a galaxy were simply flying away at high speed, the light it emits would shift for reasons similar to how the pitch of a siren changes when it moves. But cosmological redshift is tied to changes in the distance between wave peaks as they travel through expanding space. It's not caused by the galaxy's own propulsion. It's caused by the space between you and the galaxy lengthening while the light travels. This distinction might feel subtle, but it matters for how we interpret observations. It affects how we calculate distances, the age of the universe, and the rate of expansion. The mathematics behind redshift includes this stretching, allowing astronomers to reconstruct how far the light has travelled and how much the universe has changed during that journey. As scientists began applying these ideas, the image of the universe shifted from a static framework to a dynamic one. The cosmos was no longer a quiet stage where galaxies existed in fixed positions. It was an active space where distances expanded, light stretched, and the large-scale structure evolved over time. This perspective helps explain the vast gaps between galaxies, the distribution of clusters, and the overall shape of the observable universe. There's a practical element to this as well. Redshift helps determine how far away an object is when direct distance measurements aren't possible. Stars in our own galaxy can be measured using parallax or other techniques, but galaxies far beyond that require a different approach. By measuring their redshift, scientists can estimate their distance with reasonable accuracy. This makes redshift an essential part of what's sometimes called the cosmic distance ladder, a series of methods that build on each other to map the universe. But beyond its technical value, redshift tells a story about the nature of the cosmos. It shows that space isn't passive. It's not an empty container. It stretches and evolves. The distances between galaxies grow. The wavelengths of light travelling through this space change accordingly. Redshift becomes a quiet reminder that everything in the universe is part of a larger movement, one that doesn't rush, but continues steadily over billions of years. As we follow this progression, one aspect stands out. the stretching of space isn't something you can feel. It doesn't pull on your body or change the size of the things around you. It operates at scales far beyond daily experience. Only when you look at great distances does it become noticeable. This makes redshift a bridge between our quiet, familiar world and the vast, ancient stretches of the cosmos. It's the way the universe leaves small but measurable marks on the light that travels across it. In this sense, redshift acts as both a measurement and a memory. It remembers how much the universe has changed during the light's journey. It remembers how far the light has travelled. It remembers whether the expansion was slower or faster at different moments in history. Each wavelength carries a record of the path it followed. The more you think about it, the more you begin to see redshift not as a technical detail, but as a kind of cosmic footprint. It's the evidence left behind by the stretching of space. It's how we know that galaxies aren't simply drifting in isolation. They are participating in a much larger behaviour driven by the expansion of the universe. And this expansion is not only continuing but speeding up, influenced by something scientists are still working to understand. When people today look up at the night sky, they usually see it as a collection of distant lights scattered across a dark background. It's easy to forget that, for most of human history, this same sky served as a source of questions rather than answers. The patterns were familiar, the seasons shifted, and the motion of the planets could be charted with enough patience. But the deeper meaning behind those lights remained hidden. Even as telescopes improved and astronomers began identifying new objects, the clues about the universe's true behaviour remained subtle, tucked into the light itself. The night sky held evidence of expansion long before anyone realised it. We simply didn't yet know how to interpret what it was showing us. The turning point began with a shift in how scientists approached light. Before the late 1800s, most people assumed starlight was something you could describe only by brightness and colour. But with the development of spectroscopy, the technique of spreading light into a spectrum, astronomers discovered that light carries detailed information about its source. When starlight is split into its component wavelengths, it forms a pattern of colours interrupted by thin, dark lines. These lines represent specific chemical elements. Hydrogen, helium, calcium, iron, and others all leave characteristic marks. In a way, each star reveals its composition through these lines. As instruments improved, researchers noticed that in some cases these lines weren't exactly where they should be. When the same chemical signature appeared in laboratory conditions, the pattern of lines was in a certain position. But in starlight, the lines sometimes appeared slightly shifted, either toward the red end or the blue end of the spectrum. At first, these shifts were small enough to be dismissed as measurement errors or quirks in the equipment. Only later did the pattern become too consistent to ignore. These shifts weren't random. They followed a principle similar to the way sound changes when something moves relative to you. This discovery wasn't immediately tied to the universe's behaviour. Instead, it was first understood as a way to measure the motion of stars. A star moving toward Earth would show a slight shift toward blue. A star moving away would show a shift toward red. It was a practical application that allowed astronomers to track speed and direction with much more precision. But no one suspected at that point that these shifts held clues to the nature of the entire cosmos. The next major step came from observing objects far beyond the stars in the Milky Way. Before scientists understood that galaxies existed outside our own, certain faint cloudy patches in the sky were thought to be gas clouds or star clusters. When telescopes revealed spiral structures in some of these patches, curiosity grew, but it took careful study to determine that these spirals were not part of the Milky Way at all. They were separate galaxies, each containing billions of stars. The realization that the universe held countless galaxies was astonishing, but it also opened the door to new questions. Once those distant galaxies became identifiable, astronomers began applying spectroscopy to their light. The results were surprising. The galaxies almost always showed redshifts, indicating that they were moving away. Not just a few of them, not just in certain parts of the sky, nearly all of them, and as measurements accumulated, it became clear that the farther a galaxy was, the more redshifted its light appeared. This wasn't something anyone expected. The night sky, which for centuries had been treated as static, was showing evidence of motion everywhere. One of the reasons this discovery took so long is that the clues were never obvious. You can't see redshift with your eyes. You can't notice a galaxy drifting over a lifetime. Everything appears still because the distances are so vast and the changes so gradual. The clues were present all along, locked in the fine details of starlight. Without spectroscopy, they would have remained invisible. The sky didn't change. Our ability to read it did. The light from galaxies didn't just show motion. It revealed something more subtle. The wavelengths were stretched more than expected for the speeds involved. This led to the understanding that the shifting wasn't simply caused by galaxies moving through space. The expansion of space itself was affecting the light. Every beam of light travelling through the cosmos was being gradually stretched as the universe expanded. The night sky was filled with these stretched signals, but the idea wouldn't make sense until people learned how to interpret them. Even before the concept of expansion took shape, there were signs that the universe was larger and more complex than earlier generations believed. The discovery of variable stars offered important distance measurements. The mapping of nebulae showed new structures within the Milky Way. Observations of star clusters revealed age differences that didn't fit easily with a static universe. All these clues were scattered across the sky, each one offering a small hint, but none forming a complete story on its own. People tend to imagine scientific breakthroughs as sudden moments of realization, but in this case the understanding grew slowly. Early astronomers gathered more data without knowing the greater significance. They recorded spectra, positions, motions, and brightness measurements, all of which formed a foundation for future insights. The night sky was behaving in a way that didn't align with old assumptions, but no one knew yet how to connect all the observations into a single explanation. Another part of the puzzle came from studying how galaxies are distributed. Instead of being scattered randomly, galaxies formed clusters and superclusters. These arrangements suggested a long history of gravitational interactions. Yet despite gravity's influence on smaller scales, something else seemed to be shaping the larger scale behaviour. If gravity were the only force acting over cosmic distances, then large structures might have slowed or collapsed long ago. Instead, they continued drifting apart. The structures themselves were gravitationally bound, but the space between them kept widening. The night sky was telling a story of expansion long before anyone recognized it. The clues were embedded in patterns of motion and in the stretching of light. They were hints hidden in data sets that didn't yet have a framework for interpretation. When Edwin Hubble and others finally assembled the pieces, the picture became clear. The universe was expanding. Suddenly all those scattered clues aligned. Redshift, distances, distribution and brightness shifts formed a coherent explanation. This new interpretation transformed every observation that came afterward. Instead of seeing galaxies as isolated objects, astronomers began viewing them as part of a dynamic structure shaped by cosmic expansion. The night sky became a record of change rather than a static arrangement. Every point of light offered information about its distance, its past, and the space it travelled through. The idea that galaxies were drifting apart became not just a conclusion, but a fundamental part of how we understand the cosmos. In this expanded understanding, redshift plays a central role. It isn't merely a sign of motion, it reflects the stretching of space itself. Light entering a telescope carries the imprint of the universe's history. It tells us how space behaved while the light was in transit. Even when a galaxy emits light with a certain wavelength, the expansion alters the signal by the time it arrives. This ongoing stretching gives each observation a built-in reference to the universe's changing state. One of the reasons the night sky is such a rich source of information is that light travels at a finite speed. This simple fact allows us to see different parts of the universe as they were at different times. A galaxy a billion light-years away is being observed as it was a billion years ago. Light from even more distant galaxies shows us an even earlier period. The night sky becomes a timeline, not just a spatial arrangement. And redshift helps decode where each object sits along that timeline. Before astronomers understood this, the idea of looking back in time simply didn't come up. People saw stars as contemporary objects. They didn't consider that the light reaching them had been travelling for so long that it carried the history of the universe. Once this idea became clear, the night sky turned into a detailed archive. Every faint glow, every spectral line, every measured shift revealed not just distance but age. The clues had always been there in the starlight. It only took the right tools to recognise them. Another factor that made interpretation difficult in earlier eras was the assumption that the universe was static. This belief wasn't just a preference, it was tied to centuries of philosophical ideas. If the universe is unchanging, then any observed motion must be small or local. The idea that everything could be drifting apart on a grand scale didn't fit comfortably with this worldview. Even Albert Einstein initially added a term to his equations to keep the universe static. Only later did he acknowledge that the equations naturally described an expanding universe without needing adjustment. This resistance to the idea of expansion meant that many early clues were overlooked or dismissed. Redshifts were seen as motions within a fixed universe rather than signs of something more fundamental. Distance estimates were debated. The apparent faintness of distant galaxies was attributed to various causes before expansion was considered. The sky was rich with evidence, but interpretation lagged behind observation. As scientists revisited earlier measurements with new perspectives, they began to understand the full meaning of what they had observed. The universe was not only expanding, but had been doing so for billions of years. The night sky, once seen as stable, became a record of continuous change. Each galaxy offered a point on the curve of cosmic evolution. Redshift became a tool for mapping not just where things are, but how the universe has moved and grown. The ability to read these clues changed how astronomers approached research. Instead of assuming that the universe behaved in predictable, steady ways, they began looking for patterns that indicated evolution. They studied galaxy formation, star life cycles, and the growth of cosmic structures. The night sky became a laboratory for understanding how the universe reached its present state. The clues, once overlooked, became essential. Even now, the night sky continues to reveal new information. Advanced telescopes gather data at wavelengths humans cannot see. Space-based observatories measure redshifts with precision far beyond early instruments. We can now detect galaxies from the universe's earliest periods, long before the Milky Way formed. The clues hidden in their light help refine models of cosmic expansion, dark energy, and the large-scale behavior of space. There's a quiet satisfaction in knowing that these insights came from patient attention to faint signals. Nothing about the night sky shouted the truth. The stars didn't move visibly. The galaxies didn't announce their distances. The clues were embedded in tiny shifts in light, waiting for someone to notice. The universe didn't hide its behavior. It simply revealed it slowly, in ways that required careful study. The idea that galaxies could be moving away from us was already surprising when it first appeared, but what came next was even more unexpected. Once astronomers had accepted that the universe was expanding, the logical step was to assume that this expansion would gradually slow down. Gravity was the reason. Every galaxy contains mass pulls. Over time, the collective gravity of all matter in the universe should work against the expansion. Even if the universe continued spreading out, the rate should weaken little by little. That was the assumption guiding many discussions in cosmology for decades. But as new observations came in, something unusual started showing up in the data. The slowing wasn't there. Instead, the opposite pattern emerged. The expansion rate wasn't decreasing, it was increasing. The galaxies weren't simply moving apart, they were speeding up as the universe grew older. This wasn't the result anyone had anticipated. It contradicted what gravity should have been doing, and it hinted that something else was at work, something affecting the entire cosmos at once. To understand how this strange discovery happened, you have to picture the kind of observations astronomers rely on. They weren't watching galaxies move in real time. Everything in space is too far away and changes too slowly for that. Instead, they depended on light from distant supernovae. These exploding stars provided a way to measure distances on a cosmic scale. When a specific type of supernova reaches peak brightness, it shines with a known luminosity. By comparing how bright it appears from Earth, astronomers can determine how far away it is. This method became a cornerstone for measuring vast cosmic distances. It allowed researchers to build a three-dimensional sense of the universe's structure, even though the objects involved were far beyond anything that could be reached directly. The brightness wasn't interpreted casually. It required careful calibration, comparisons, and cross-checks with other distance indicators. Over the years, these techniques became reliable enough for scientists to trust their conclusions. In the 1990s, two independent research teams set out to measure the rate of cosmic expansion by studying these distant supernovae. Their goal was to see whether the universe was slowing down and by how much. They expected that the farther back in time they looked, the stronger gravity's influence would appear. A universe that began with rapid expansion should show signs of deceleration as time went on. The teams collected data from many supernovae at different distances, each one offering a tiny piece of the cosmic timeline. When the results were analysed, something didn't add up. The distant supernovae were dimmer than predicted. Dimmer meant farther away, and farther away meant the expansion had been slower in the past. If it had been slower then and faster now, it meant the universe was speeding up. The light from those ancient explosions showed that billions of years ago the galaxies weren't spreading apart as quickly as they are now. Instead of slowing under the pull of gravity, the expansion had begun to accelerate. This was a stunning conclusion. It suggested that some unknown influence was pushing galaxies outward. Researchers rechecked their data, recalculated distances, and examined every possible source of error. But both groups, working independently and unaware of each other's results, had reached the same answer. The acceleration was real. The surprise wasn't just scientific. It challenged long-held expectations about how the universe should behave. A universe that slows down feels intuitive. Throw a ball and it slows. Send a spacecraft into space and it eventually drifts with less momentum unless something pushes it. Even the expansion itself had seemed like a leftover effect from the early universe. But a universe that speeds up without any external force didn't match familiar patterns. The only explanation that fit the data was that something was acting against gravity. This mysterious influence wasn't just cancelling gravity in some regions, it was dominating the expansion across the entire universe. And because it couldn't be explained by any known form of matter or energy, it received a placeholder name: dark energy. At first, dark energy wasn't a theory, it was simply a label for whatever was causing the acceleration. No one knew what it was made of, or how it worked. The name reflected the lack of understanding. It was as if the universe had revealed an unexpected behaviour, and scientists needed a new term just to describe the effect. One of the most puzzling aspects of this discovery is that dark energy doesn't weaken as the universe expands. Most forms of matter and radiation become less dense as space grows. Spread a gas out and it thins. Spread light out and it becomes less concentrated. But dark energy appears to stay constant in its density. That means as the universe grows, dark energy occupies more total space, increasing its overall effect. It's similar to filling a room with something that always remains equally dense, no matter how large the room becomes. The more space there is, the stronger the influence becomes when compared with gravity, which weakens over distance. This property helps explain why the acceleration started relatively late in cosmic history. In the early universe, matter was dense. Gravity dominated, galaxies formed, clusters emerged. The structures we see today were shaped by the pull of mass. But as the universe expanded and matter became more spread out, gravity's influence weakened. Once enough space had stretched out, dark energy's effect became stronger by comparison. Eventually, it overtook gravity on the larger scales and began to accelerate the expansion. This happened billions of years after the first stars formed. Nothing abrupt marked the transition. It was a gradual shift as the balance of influences changed over time. If this was simply a matter of galaxies moving faster, the data wouldn't show such a uniform pattern. Instead, the acceleration appears everywhere, affecting all regions of space equally. This uniformity strongly suggests that dark energy is a property of space itself. It isn't something sitting in particular locations. It doesn't clump like matter or accumulate in structures. It acts evenly across all of space at all times. This uniform behavior is what makes cosmic acceleration so strange. Nothing else we know of behaves this way. Matter pulls inward through gravity. Radiation thins as it spreads. Dark matter influences structure but doesn't push anything outward. Dark energy, however, seems to apply a kind of steady outward pressure that becomes more significant as space expands. And because space continues to grow, this effect becomes increasingly noticeable. The idea didn't settle quickly. Many scientists were skeptical at first. It's a common part of science for new discoveries to face scrutiny, especially when they seem to contradict established expectations. Alternative explanations were considered. Perhaps the supernovae weren't as uniform in brightness as assumed. Maybe dust between galaxies made distant supernovae appear dimmer than they truly were. Perhaps the universe had a geometry different than the one being used for calculations. All of these possibilities were explored, tested, and compared with observations. None fit the data as well as the conclusion that the expansion was accelerating. Other measurements began to support the same picture. Observations of the cosmic microwave background, the faint afterglow of the early universe, contained patterns that matched a universe dominated by dark energy. Studies of galaxy clusters helped confirm it. Over the years, independent lines of evidence strengthened the conclusion. Even with this growing support, cosmic acceleration remains one of the most unusual and challenging discoveries in modern cosmology. It forces us to rethink how the universe works at the larger scales. Gravity had always been the main sculptor of cosmic structure. Now something else had joined the story, something more subtle but equally influential. The galaxies were drifting apart faster over time, and the night sky held the quiet but unmistakable signs of this change. It's interesting to consider the nature of discoveries like this. The acceleration of the universe isn't something anyone can feel or observe directly. It's not like a change in the weather or a shift in temperature. It's something detected through patterns in light that took billions of years to reach Earth. The signals are faint, the distance is immense, and the change is subtle. Yet from these small pieces of evidence, a vast new understanding emerged. One of the reasons this discovery feels so unusual is that it suggests a different kind of behavior for the universe than what intuition provides. Normally, motion slows when forces oppose it. A speeding car encounters friction. A thrown object loses momentum. Even planetary orbits follow predictable paths. The idea that something could expand more quickly without any clear source of energy or motion challenges these familiar patterns. The universe behaves on a scale where intuitive expectations do not always apply. This realization encouraged many new investigations. Scientists began searching for explanations rooted in quantum physics, general relativity, and theories of fields that might permeate space. Some possibilities involve vacuum energy, a small but persistent energy associated with empty space. Others involve fields that change slowly over time. Some ideas explore the possibility of additional dimensions or new types of interactions. None of these ideas has yet provided a complete answer, but each one explores a different angle of the problem. What remains consistent across all models is the need to explain the observed acceleration. The galaxies genuinely are moving apart more quickly now than in the past. The expansion rate is not constant. The behavior isn't slowing, it's increasing, following a pattern seen in the light from distant supernovae and confirmed through multiple independent methods. This change affects our understanding of the future as well. If the acceleration continues, the universe will grow more diffuse over time. Galaxies outside our local group may drift so far away that their light will no longer reach us. The night sky that seems full today may gradually become emptier over very long timescales. This isn't something anyone alive will witness, but it's part of the long-term behavior that follows naturally from the acceleration. The discovery of cosmic acceleration also highlights something about how science progresses. It doesn't always advance through dramatic, immediate changes. Sometimes it requires years of collecting data, comparing measurements, checking for errors, and refining models. The supernova observations didn't shout their meaning. They offered a subtle discrepancy. The brightness didn't match expectations, the redshift didn't align with predicted distances. Those mismatches pointed toward a larger truth. Once the acceleration was recognized, it changed the framework for understanding the universe. Many earlier puzzles made more sense in this new context. Observations of the cosmic microwave background fit better. Patterns in galaxy distribution became easier to interpret. Measurements that once seemed awkward aligned neatly with the idea of a universe dominated by dark energy. And yet, even with this coherence, the acceleration poses unanswered questions. What exactly is dark energy? Why does it behave the way it does? Is it truly constant in density, or could it evolve over time? Does it come from the quantum vacuum or from a field that fills all of space? Is it related to gravity or something completely different? These questions don't yet have clear answers, but each one guides further research. What makes this especially compelling is that the acceleration is not a minor effect. It shapes the universe at the larger scales. It influences the overall curvature of space. It determines the long-term behavior of cosmic expansion. It affects how structures form and how galaxies move relative to each other. Something that does all of this must be fundamental, yet we still only know it through its effects, not through direct detection. As we continue through this exploration, this strange discovery becomes a key turning point. The universe's acceleration connects directly to redshift, to cosmic expansion, and to the mystery of dark energy. Each part builds on the last, and the story that emerges is one of a universe that doesn't act in the simple, slowing way people once assumed, but instead grows more expansive as time passes. Most ideas in science begin with something we can point to, measure directly, or observe without too much difficulty. Dark energy is unusual because it emerged from a gap in understanding rather than from a clear sign of its own existence. Scientists didn't detect it through a visible signal or a distinct pattern. They inferred it from a discrepancy. Something unexplained was influencing the universe. Something subtle but powerful had begun shaping the expansion in a way nothing else could account for. And although the evidence for this influence grew steadily, the nature of it remained hidden. To see how such an idea developed, imagine starting with the assumption that the universe should slow its expansion gradually over time. This assumption wasn't arbitrary. It came from the influence of gravity. Gravity pulls matter together. If the universe contains matter, and it does, then the expansion that began shortly after the Big Bang should weaken as billions of years pass. In a universe filled with stars, galaxies, gas and dark matter, gravity should act like a brake. It might not stop the expansion entirely, but it should slow it. This expectation became part of nearly every model of cosmic evolution for many decades. So when astronomers discovered that the expansion was not slowing, but accelerating, the entire framework had to be reconsidered. Nothing about ordinary matter or known forces could explain the acceleration. Something else had to be present, something with a consistent push that didn't weaken as space grew larger. What made this realization so striking is that dark energy does not match any familiar category. It isn't made of particles like the matter we see. It doesn't behave like radiation. It doesn't gather or clump in ways gravity can detect directly. Instead, it appears to act uniformly across all space and remains steady in its density even as the universe expands. This combination of properties makes it unlike anything else in the cosmic inventory. The name dark energy came later, after the behavior was clear, but the underlying cause was not. The name itself doesn't explain anything. It simply acknowledges that whatever is responsible for the acceleration operates invisibly and affects the energy balance of the universe. The word dark reflects our lack of direct detection. The word energy hints at its influence on the expansion. Beyond those hints, the name describes the mystery rather than solving it. One interpretation of dark energy connects it to something called vacuum energy. In quantum physics, the vacuum isn't empty space. Instead, it contains constant fluctuations of fields, momentarily producing and annihilating particles that exist too briefly to observe directly. These fluctuations carry energy. The idea that empty space has energy might seem strange at first, but it fits within quantum theory. If space has energy, even in its emptier state, this energy might act as a pressure that affects the expansion of the universe. There's a challenge with this explanation though. When theoretical calculations attempt to estimate the energy of the vacuum, the results tend to be far larger than what cosmic measurements allow. The observed amount of dark energy is extremely small. Theoretical estimates are enormously larger, off by many orders of magnitude. This mismatch suggests that our understanding of vacuum energy is incomplete. It might be related to dark energy in some way, but the connection is not settled. Another possibility involves a slowly changing field that fills all of space. In physics, fields aren't necessarily visible or tangible. They are mathematical descriptions of influences that exist everywhere. The best known example is the gravitational field. Gravity doesn't require physical material to be present in every location. Its influence exists even in empty space. Similarly, dark energy might come from a field that has a constant or slowly varying value throughout the universe. Such a field could create a type of pressure that promotes expansion. If it changes only gradually, its influence might strengthen relative to matter and radiation as the universe grows older. This idea helps explain why cosmic acceleration began after billions of years rather than immediately after the Big Bang. In the early universe, matter was dense and gravity was dominant. As expansion spread matter apart, this new influence could rise in prominence, but even this explanation remains speculative. No direct detection of such a field exists. It remains an idea that fits some data but lacks a clear experimental signature. Scientists continue to explore it because it offers a potential framework, but more evidence is needed to confirm or reject it. A third avenue of investigation considers whether dark energy might not be energy at all, but instead a sign that our understanding of gravity is incomplete. General relativity, Einstein's theory of gravity, has been remarkably successful in explaining everything from planetary orbits to black holes. Yet it was developed long before the concept of cosmic acceleration. It's possible that on the larger scales, gravity behaves slightly differently than the equations predict. If gravity weakens at extremely large distances or acts differently across vast expanses, this behavior might mimic the effects attributed to dark energy. Researchers have proposed modified gravity theories to explore this possibility. Some of these models add extra terms to Einstein's equations. Others introduce new interactions or dimensions. None has yet proven to be a better fit than general relativity combined with dark energy, but the exploration continues. This line of inquiry recognizes that the acceleration might signal a gap in the current framework rather than the presence of a new form of energy. It's a reminder that even well-tested theories can require adjustments when new evidence appears. What unifies these possibilities is that they all attempt to explain the same phenomenon: cosmological acceleration. Regardless of whether the cause is vacuum energy, a new field, or a modification of gravity, the goal is to account for the observed behavior of galaxies drifting apart more rapidly over time. The search for an explanation continues because no model is fully satisfactory. Each offers strengths and weaknesses. Each matches some aspects of the data, but leaves others unresolved. This makes dark energy one of the most significant open questions in physics. It affects not only the current behavior of the universe, but also its future. If dark energy remains constant in its density, the expansion will continue to accelerate. Galaxies will grow more distant. The light from faraway regions will stretch into wavelengths too long to be detected. Over unimaginably long periods, other galaxies may slip beyond our observable horizon. The universe will grow increasingly diffuse, and the structures we see today will become isolated within their own regions of space. If dark energy changes with time, the picture could look different. It might strengthen, weaken, or evolve in unexpected ways. The expansion might change its rate. The large-scale behavior of the universe might follow trajectories we haven't yet predicted. Because dark energy shapes the overall structure of the cosmos, its nature determines long-term cosmic evolution. It's worth noting that the acceleration itself is subtle. The expansion of space is already gentle at human scales. The acceleration is even more delicate. You wouldn't notice any change in the distances between objects in your daily life. Gravitationally bound systems like planets, stars, and galaxies are protected from the expansion by their own internal forces. Only at vast distances, where gravity weakens, does the expansion take hold. And only over billions of years does the acceleration become noticeable. This makes dark energy especially elusive. It acts everywhere, yet nowhere in a way we can feel directly. It leaves no local trace. Its influence becomes apparent only when studying the universe at its larger scales. The evidence lies in redshift patterns, the distribution of galaxies, and the shape of the cosmic microwave background. These faint signals are the only way to observe its presence. Despite its mysterious nature, dark energy composes the majority of the universe. Taken together, matter and radiation account for only a small fraction of the total energy content. Dark matter contributes more, influencing the formation and behavior of galaxies. But the largest share appears to belong to dark energy. This means most of the universe's energy budget is tied to something we don't understand. This realization changes how we view the cosmos. What we see, stars, planets, gas clouds, galaxies, is only a small portion of what exists. The visible universe is shaped by forces we do not yet fully grasp. That perspective can feel unfamiliar at first, but it also reflects the nature of scientific exploration. Many discoveries start with things we can measure before revealing deeper layers that challenge earlier assumptions. As research continues, new tools are being developed to study dark energy. Some rely on mapping the positions and motions of millions of galaxies. Others examine the effects of gravitational lensing, where light from distant objects bends around massive foreground structures. Some projects focus on measuring cosmic expansion with greater precision. Each approach offers a different angle on the same underlying mystery. The aim is to gather enough evidence to distinguish among the possible explanations. If the expansion rate changes in a particular way, it might support the idea of a slowly varying field. If certain patterns emerge in the distribution of galaxies, they might indicate whether gravity behaves differently at large scales. If measurements of the cosmic microwave background show particular features, they might strengthen the case for vacuum energy. The path forward is gradual. No single observation is expected to resolve the question entirely. Instead, progress will come from a combination of methods, each one narrowing the possibilities. This approach mirrors how the acceleration was discovered in the first place, through careful attention to multiple lines of evidence that point toward a shared conclusion. What stands out about dark energy is that it remains one of the quietest influences on the universe and one of the most significant. It doesn't reveal itself through direct interaction. It doesn't shine, pull, or collide. Yet it shapes the fate of everything. It determines how space expands, how galaxies move apart, and how the long-term history of the universe unfolds. Even though the name suggests something hidden, the influence of dark energy is evident in the way light reaches us from across the cosmos. The stretching of space leaves measurable marks. The accelerating expansion appears in every direction. The challenge is not detecting that something is happening. The challenge is identifying what the cause is. When most people hear the phrase empty space, they imagine nothing at all. A blank region without substance, activity, or structure. A place where nothing is happening. This idea works fine for everyday experience. Air can seem empty. A quiet room can feel still. Even the spaces between objects in your home appear inactive. But on the scale of the universe, the concept of emptiness becomes more complicated. What seems empty isn't truly empty. What looks still isn't entirely still. And the deeper scientists looked into what space actually is, the more they realized it behaves in ways that are far from simple. One of the strangest parts of modern physics is the recognition that empty space has properties. It isn't a stage where events happen. It participates in the events. Space can stretch, bend, ripple, and expand. It can influence the motion of objects. It can carry energy. It can shift in ways that affect how light moves. And even when nothing appears to occupy it, space itself may hold subtle forms of activity that can't be detected directly, but still influence the universe as a whole. This idea didn't appear all at once. For centuries, space was treated as a passive backdrop. The planets moved. The stars sat in fixed positions. Comets travelled along predictable paths. And the space between them seemed like a silent medium with no role beyond holding everything in place. Even when people began studying gravity more deeply, space still seemed independent of the forces at work. Gravity was considered a pull between objects, not a feature of the space itself. That changed gradually, especially with the development of general relativity. Einstein's equations describe gravity not as a force but as a shape. Mass and energy curve space. Objects follow paths shaped by this curvature. Space isn't flat or empty. It responds to the matter within it. This idea helped explain the motions of planets and the bending of light near massive objects. It suggested that space has a kind of flexibility, something that can change and react. The notion of emptiness began shifting at that point, even though the full implications would only become clear much later. As scientists began studying large-scale cosmic structures, they noticed that galaxies weren't scattered randomly. They formed clusters, filaments, and voids. The voids appeared empty, but even these vast regions weren't truly blank. They contained dark matter, weak fields, and low-density gas. They weren't stretches of pure nothingness. They were simply less crowded than other regions. Still, these structures didn't yet reveal anything strange about empty space itself. They mainly showed how matter shaped space, not how space behaved on its own. The turning point came when observations of distant supernovae suggested that the universe's expansion was accelerating. Something seemed to be influencing space in a consistent, pervasive way. The acceleration couldn't be explained by matter, since matter exerts gravitational attraction and should slow expansion, not speed it up. Whatever was causing the acceleration had to be tied directly to space itself. It couldn't be isolated to particular regions or objects. It had to operate everywhere at once. This realization forced scientists to reevaluate what empty space was doing. If empty space were completely inert, the expansion would follow predictable patterns dominated by gravity. But the expansion wasn't following those patterns, it was accelerating. The simplest explanation was that empty space contains energy, a form of energy that doesn't thin out as the universe grows. This energy, distributed evenly across all space, would push outward, causing the expansion to speed up. It didn't need to interact with matter, it only needed to exist within the structure of space itself. This idea fits well with one of the predictions from quantum mechanics, which states that fields in empty space fluctuate constantly. They never settle quietly. Even when they contain the lowest possible energy, they still produce tiny temporary disturbances. These fluctuations arise and vanish too quickly and too subtly for direct detection, but they exist within the mathematics of quantum theory. If these fluctuations carry even a small amount of energy on average, that energy would affect how the universe expands. The difficulty lies in matching theory with observation. Quantum calculations often predict far more vacuum energy than observations allow. The theoretical estimates exceed measured values by enormous amounts. This discrepancy is one of the biggest unsolved problems in physics. If empty space contains energy, why does it appear at such a small level? Why does it influence the universe in such a quiet but persistent way? The answers remain unclear, and the mismatch between theory and measurement shows that something important is still missing from our understanding. Even with these open questions, the idea that empty space has energy has become a central part of cosmology. This energy is often associated with dark energy, the influence responsible for the universe's accelerating expansion. But dark energy is only one possibility. Some researchers believe the energy could come from a field that permeates space and evolves slowly over time. Some think it could reflect a property of space that hasn't yet been incorporated into existing theories. Others believe it might indicate that gravity behaves differently on large scales than expected. What unites all these ideas is the recognition that space itself isn't idle. Even when nothing appears to fill it, space has structure and influence. Its behavior shapes the destiny of the cosmos. It determines how galaxies move, how light travels, and how the universe changes over billions of years. The idea that empty space can expand also challenges earlier assumptions. Before the concept of cosmic expansion became well known, many people imagined space as a container that held matter. A container doesn't change its size, it simply sits there. But the universe doesn't behave like a container. Instead, space stretches. This stretching increases the distance between galaxies, even if the galaxies themselves don't move through space. The phenomenon isn't caused by motion in the ordinary sense. It's caused by a change in the underlying geometry. This perspective reshapes how we think about movement and distance. When galaxies drift apart because space stretches, they aren't pushing away from each other. They're following the changing structure of space. Even if a galaxy tried to resist the expansion, it couldn't. The expansion is not a force acting on galaxies. It's a property of space itself. No amount of motion within space can counteract it. This distinction helps explain why expansion doesn't affect objects bound together by gravity. Planets, stars, and galaxies stay intact because local forces override the stretching. Only at larger scales does the expansion become noticeable. When scientists talk about what empty space is doing, they're often referring to these large-scale behaviors. They're looking at how space expands, how it carries galaxies along with it, and how it contributes to cosmic acceleration. But there are other smaller-scale effects as well. Quantum fluctuations in empty space can influence particle behavior. Virtual particles, which appear briefly in these fluctuations, can affect how forces operate. Sometimes these effects are detectable, such as in the case of the Casimir effect, where metal plates placed very close together in a vacuum experience a tiny force caused by changes in vacuum energy between them. These small-scale effects don't explain dark energy, but they support the idea that empty space is not empty in any absolute sense. It has properties, it has behavior, it contains fields that interact in subtle ways. These interactions matter when trying to understand how the universe behaves. They provide hints about the deeper structure of reality, even when the exact connections remain uncertain. Another aspect of empty space becomes apparent when considering the shape of the universe. Space isn't necessarily flat. It can have curvature depending on the amount of matter and energy within it. Observations suggest that the universe is close to flat, but even slight deviations would reflect important differences in how space behaves. These differences would influence the way expansion unfolds and how the distribution of galaxies changes over time. The shape of space isn't static. It evolves with the universe. The recognition that space can curve and expand leads to a broader understanding of it as something dynamic. It responds to matter and energy. It changes as the universe evolves. It carries imprints of previous cosmic phases. It influences the future. This dynamic nature makes the idea of nothing happening in empty space less accurate. Even in regions far from galaxies, space is part of the universe's ongoing evolution. As researchers continue to study empty space, they explore questions that extend beyond cosmic expansion. They investigate how fields behave in extreme conditions, such as near black holes, or during the early moments of the universe. They look for signatures of interactions that might reveal new aspects of fundamental physics. They consider how the structure of space might connect to quantum gravity, a theory still under development that aims to unify general relativity and quantum mechanics. All of these areas rely on understanding what space is doing at levels far more detailed than daily experience can reveal. The search for answers takes different forms. Some studies use large-scale surveys of galaxies to map how structures evolve. Others examine the cosmic microwave background for subtle patterns. Still others use precise measurements of gravitational lensing to detect how space bends around massive objects. Each method provides a new way of observing the behavior of space. Each one contributes a piece to the larger picture. Even though many questions remain, one conclusion stands out. Empty space is one of the most active components of the universe. It expands, it carries energy, it shapes motion, it responds to matter. It influences the fate of galaxies, and its behavior remains one of the most important puzzles in modern physics. If you imagine the universe at its largest scale, stretching out in all directions, it's easy to forget that everything in it is connected by forces that have been at work since the beginning. One of those forces has shaped the formation of galaxies, stars, planets, and the structures we see through telescopes. Gravity, steady and unwavering, has been the sculptor of the cosmos from the earliest moments. Yet as vast as its influence is, the expansion of the universe presents it with a challenge that grows more difficult over time. The faster space stretches, the harder gravity must work to pull things together. Understanding how this struggle plays out offers an important way to see why cosmic acceleration remains one of the most significant discoveries in modern astronomy. When people first learned about gravity as a physical force, the idea was applied mainly to everyday motions. Objects fall because gravity pulls downward. The planets orbit the sun because gravity holds them in place. Even tides rise and fall in part because of gravity's influence. It wasn't until scientists observed how stars moved in galaxies and how galaxies interacted with one another that gravity revealed its broader role. At small scales, it keeps your feet on the ground. At large scales, it organizes matter into structures that span millions of light years. The early universe, shortly after the Big Bang, was extremely dense. Matter was packed tightly. In those early conditions, gravity was overwhelmingly influential. Small variations in density created regions that attracted more matter. These regions grew over time, eventually forming the first stars and galaxies. Without gravity, these structures would never have taken shape. But with gravity pulling inward, matter clumped, cooled, collapsed into stars, and began the process of building complex cosmic architecture. Gravity's influence relies on mass. The more mass in a region, the stronger the pull. This relationship helps explain why galaxies form in certain places and not others. Areas with slightly higher density attracted more matter, and as those regions grew, gravity kept pulling material toward them, reinforcing the pattern. These structures didn't appear instantly. They developed slowly, shaped by a constant inward pull. Even today, gravity continues to shape the behavior of galaxies, influencing how stars move within them and how galaxies interact with one another over long periods. But while gravity was shaping the internal structures of the universe, something else was affecting the overall motion of galaxies across great distances. The expansion of the universe began early and never stopped. As space stretched, galaxies moved apart not because they were flying through space with their own momentum, but because the space between them kept increasing. This expansion didn't disrupt the local formation of structures because gravity was strong enough to hold matter together in those regions. But on scales larger than the reach of gravitational binding, the expansion steadily increased the separation between galaxies. For a long time, scientists believed that gravity's influence would eventually slow this expansion. They didn't expect the expansion to stop completely, but they assumed the speed of separation would gradually decrease as mass continued pulling inward. After all, gravity works on every particle, every star, every galaxy. The force may weaken with distance, but it doesn't disappear entirely. It seemed reasonable that gravity, acting on all the matter in the universe, would counteract at least some of the expansion. This expectation shaped many early models of the universe's future. Some models suggested expansion would slow so much that the universe might eventually reach a steady state. Others suggested that if matter were dense enough, gravity might eventually pull everything back together in a collapse. Still others predicted that the expansion would continue forever, but with diminishing speed. All of these models shared the idea that gravity would always oppose the expansion. The struggle seemed straightforward. Expansion pushes outward, gravity pulls inward, and those two influences determine the universe's long-term behavior. The discovery of cosmic acceleration changed that picture dramatically. Gravity wasn't slowing the expansion. Instead, galaxies were moving apart faster over time. The expansion wasn't weakening, it was gaining strength. This unexpected behavior made gravity's role more complex. It wasn't a matter of gravity losing its ability to pull. Gravity still operated with the same strength it always had. What changed was the relative influence of gravity compared to something else permeating the universe: dark energy. Dark energy's presence means that gravity is no longer the only large-scale influence on the expansion. As space grows, the relative share of dark energy grows as well. Over time, this additional influence becomes stronger compared to gravity, not because gravity weakens, but because dark energy remains consistent while matter becomes more spread out. This shift in balance explains why the expansion can accelerate. Gravity still pulls inward, but its reach over large distances becomes less significant as dark energy dominates the behavior of space itself. To understand how this struggle unfolds, imagine the distribution of matter across the universe. Galaxies cluster in certain regions. Filaments of matter stretch between clusters. Vast voids occupy enormous volumes. Within clusters and galaxies, gravity easily keeps matter bound. No amount of cosmic expansion can tear apart a galaxy or loosen a star from its orbit around the galactic center. Gravity remains dominant there. But as you examine distances beyond those structures, gravity's influence becomes weaker. Matter becomes sparse. The expansion of space becomes noticeable, and eventually, dark energy's influence surpasses gravity's reach. This doesn't mean gravity becomes irrelevant. It still holds every dense structure intact. It shapes the orbits of stars and the dynamics of clusters. It determines how matter collapses to form new objects. But when considering the universe as a whole, the balance shifts. Gravity works locally. Dark energy works everywhere at once. The result is a universe where the small-scale world remains stable, while the large-scale world accelerates outward. One interesting aspect of this struggle is that it wasn't always tilted in favor of dark energy. In the early universe, matter was much more concentrated. Gravity dominated nearly every region. As matter expanded outward, its density decreased. Meanwhile, the energy associated with dark energy remained constant. Eventually, matter became thin enough across the cosmos that dark energy began to outweigh gravity's large-scale influence. This transition didn't happen suddenly. It unfolded over billions of years. But once dark energy took over, the expansion began accelerating, and gravity's large-scale influence became secondary. This change also explains why cosmic acceleration wasn't detected earlier. When the universe was young, gravity's pull was strong enough to influence the overall rate of expansion. Only when matter became spread out enough did the balance shift significantly. By the time astronomers measured distant supernovae, the universe was already in a phase where dark energy dominated. The evidence showed not only that the expansion was ongoing, but that it had changed course and begun speeding up. It's worth noting that gravity's struggle isn't a battle in any literal sense. There's no confrontation between two forces. Instead, it's a matter of how different influences shape the universe at different scales. Gravity binds matter on local and intermediate scales. Dark energy shapes the geometry of space on the larger scales. Both are part of the cosmic picture, but their roles differ depending on the distance involved. This distinction helps explain why the night sky looks the way it does. Stars form within galaxies because gravity pulls gas clouds together. Galaxies form clusters because gravity draws them into groups. But the clusters themselves drift apart because the space between them expands. Observations of galaxy distribution reveal this pattern clearly. Structures remain coherent internally while drifting apart from other structures over time. The balance between gravity and expansion determines the arrangement we see. Another important aspect of gravity's role is how it influences the rate of structure formation. In the early universe, matter formed stars and galaxies at a faster pace. As expansion continued, matter became more spread out, reducing the ability of gravity to pull it together into new structures. Over time, the rate of formation slowed. This doesn't mean new stars no longer form, they still do. But the overall dynamics reflect a universe where gravity is competing against the expanding volume of space. The presence of dark energy further reduces the availability of matter for collapse. As galaxies drift apart, the distance between potential sources of matter grows. Gravity can't reach across the widening gaps. This means the future of structure formation becomes more limited. Rather than forming new massive clusters or enormous galaxies, the existing structures will persist while others move beyond their gravitational reach. Gravity can hold onto what it has locally, but can't bridge the growing emptiness between widely separated regions. This trend continues as the accelerating expansion progresses. Regions that were once close enough to exchange material become isolated. Light from distant galaxies becomes increasingly stretched. Eventually, the accelerated expansion may carry some galaxies beyond the horizon of observability, meaning their light will no longer reach us. Gravity remains active within local groups, but it can't influence the large-scale structure of space dominated by dark energy. While this may seem like gravity is slowly losing its relevance, the truth is more nuanced. Gravity still provides the framework for understanding how matter behaves. It shapes the long-term stability of stars, the orbits of planets, and the interactions between galaxies within clusters. It binds black holes, neutron stars, and planetary systems. Without gravity, none of these structures could have formed or persisted. Gravity's role remains essential, even as the universe expands more rapidly. The struggle between gravity and expansion also helps illuminate the future of the cosmos. If dark energy continues to dominate with its current behavior, the expansion will keep accelerating. Galactic clusters will remain intact, but will drift farther apart from other clusters. The observable universe will shrink in practical terms, as fewer galaxies remain close enough to be seen. Over extremely long timescales, only the gravitationally bound local structures will remain visible. Everything else will drift into regions where the light no longer reaches us. There are alternative possibilities as well. If dark energy changes over time, the balance could shift again. The acceleration might slow, it might increase more strongly, it might evolve in ways that alter gravity's ability to influence large regions. These possibilities remain open, and scientists continue to investigate them through observations of distant galaxies, gravitational lensing patterns, and the cosmic microwave background. What becomes clear from all of this is that the universe's behaviour is not determined by one influence alone. Gravity and dark energy both shape the cosmos, each in its own domain. Gravity dominates the small and intermediate scales. Dark energy dominates the large scales. Their combined effects form the universe we observe today. This layered structure of influence also reflects how science approaches complex problems. Understanding the universe requires looking at its behaviour across multiple scales. Measurements of star orbits reveal one part of the story. Observations of galaxy clusters reveal another. Studies of cosmic acceleration reveal yet another. When combined, these layers offer a cohesive picture. Even though gravity doesn't determine the expansion's long-term trajectory, it remains essential for the structures that give the universe its richness. Stars continue forming, planets continue orbiting, clusters remain bound, galaxies interact and merge. These processes will continue for billions of years, unaffected by the overall expansion. Gravity's role remains steady within its domain. When scientists started asking what shape the universe might have, the question wasn't about something that could be drawn or pictured in the usual way. It wasn't about imagining the universe as a sphere or a cube or some familiar object. The idea was much more subtle. It involved understanding how space behaves, how distances change, and how the structure of the cosmos directs its own evolution. The shape wasn't something you could see from the outside. It was something you had to infer from how light travels, how galaxies are arranged, and how the expansion unfolds across billions of years. The concept of shape in this context refers to geometry on the largest possible scales. Instead of thinking about the surface of an object, it means asking whether space is curved, how that curvature affects the motion of galaxies, and what it implies for the future. It turns out that the universe can have different geometries depending on how much matter and energy it contains. These geometries influence everything from the way triangles behave to the paths light takes across immense distances. At smaller scales, inside a room, across a city, or even through the solar system, space appears flat. Lines run straight. Distances behave as expected. But on cosmic scales, where the combined effects of gravity and expansion accumulate, space might curve in subtle ways. The challenge is that these curvatures are far too gentle to notice with ordinary measurements. Only by looking across large stretches can scientists detect small differences between what would happen in a perfectly flat universe and what actually happens. Before researchers began gathering precise data, there were three broad possibilities for the universe's overall shape: closed, open, or flat. These terms describe the curvature of space. A closed universe curves inward like the surface of a sphere. An open universe curves outward loosely like a saddle. A flat universe has no overall curvature. The shape depends on the balance between energy, matter, and expansion. More matter and energy can create positive curvature. Less leads to negative curvature. A specific balance results in flatness. The geometry affects how the universe evolves. In a closed geometry, the total amount of matter and energy is high enough that gravity could eventually overcome expansion. If this were the case, the expansion might slow, halt, and then reverse. In an open geometry, the expansion would continue infinitely without ever slowing enough to stop. In a flat geometry, the universe would expand forever, but at a rate that changes based on its contents. These three broad possibilities framed much of the early work in cosmology, because they represented different long-term outcomes. The challenge was determining which of these possibilities matched the actual universe. Since the geometry affects how light moves, scientists looked at distant objects to gather clues. If the universe were closed, light travelling over vast distances would converge slightly. If it were open, it would diverge. If it were flat, it would travel along straight paths. Measuring these effects required examining the distribution of galaxies, the the patterns in the cosmic microwave background, and the behaviour of distant supernovae. Each of these provided hints about the geometry. The most useful clues came from the cosmic microwave background, a faint glow left over from the early universe. This radiation contains slight temperature variations that reflect how matter was distributed shortly after the Big Bang. These variations create patterns on the sky that depend on the geometry of space. When scientists measured these patterns with great precision, the results strongly suggested that the universe is flat, or extremely close to flat. The margin of error is small, but the current evidence points toward flatness. A flat geometry means that space does not bend overall. It doesn't curl back on itself like a closed universe, nor does it stretch outward like an open universe. This doesn't mean space is simple or static. Local regions still curve because of mass. Gravity still shapes the paths of objects. But on the larger scales, the universe behaves as though it has no net curvature. This result was surprising in some ways because it suggested that matter and energy have a particular balance. Too much would have created positive curvature. Too little would have created negative curvature. The near flatness suggests a very specific distribution. However, the presence of dark energy complicates the picture. Dark energy affects how the universe expands, but does not gather into structures the way matter does. Because it acts uniformly, it influences the geometry differently from ordinary matter. When dark energy became part of the model, it changed how scientists interpreted the curvature. It allowed for the universe to remain nearly flat even if the amount of matter was not as high as earlier theories required. It became clear that dark energy was not just an addition to the cosmic inventory, but a major factor in determining the universe's shape and future. One of the interesting consequences of a flat universe is how it influences the universe's long-term evolution. Without dark energy, a flat universe would expand forever, but slow over time. With dark energy, the expansion accelerates. The future becomes dominated by the behavior of space itself. Galaxies drift apart faster. The large-scale structure changes in ways that depend on how dark energy behaves over time. If dark energy remains constant, the expansion will continue accelerating. If dark energy changes, the paths could differ. Even though the universe appears flat, the exact behavior depends on the details of dark energy. If dark energy increases slowly, the expansion could accelerate more strongly. If it decreases, the expansion might slow. If it evolves unpredictably, the geometry could change gradually over extraordinary timescales. These possibilities form different paths the universe might take. Each one arises from how space, matter, and dark energy interact. Another part of the story involves the idea of horizons. Because space expands, there are regions whose light may never reach us. As the universe accelerates, this horizon can shrink in practical terms. Even though the universe is flat, the paths light can take are affected by the expansion. Galaxies moving away too quickly may drift beyond the point where their light can reach Earth. In the distant future, fewer galaxies will remain visible. This doesn't change the geometry, but it affects what we can observe. Thinking about the shape of the universe also raises questions about what lies beyond the observable region. The part we can see is limited by the age of the universe and the speed of light. Beyond that boundary, space continues. The geometry there is assumed to be the same because there's no evidence of major differences, but it remains unobservable. Even so, the shape of the universe applies to the whole, not just the part we see. The consistency of the cosmic microwave background suggests that conditions outside the observable region are similar. Some models suggest that space may be finite even if it appears flat. This might seem contradictory at first, but certain geometries allow for a flat space that loops back on itself in complex ways. In such a universe, travelling far enough in one direction could theoretically bring you back to your starting point. This idea requires specific mathematical conditions and has not been confirmed. It remains an interesting possibility but lacks direct evidence. Most observations are consistent with an infinite flat universe. but the finite flat option remains open because it would appear nearly identical from within. The shape also influences how density fluctuations evolve. Small variations in matter density in the early universe grew into galaxies and clusters. The geometry played a role in determining how quickly these fluctuations grew. A closed universe would have favoured different growth rates. An open universe would have caused clusters to evolve differently. The nearly flat geometry matches the distribution of structures we observe today. This consistency between models and observations strengthens confidence in the flat interpretation. Understanding the shape helps clarify how the universe might behave going forward. Since it appears flat and dark energy dominates, expansion will likely continue. The paths it can take depend on how dark energy evolves. If it remains steady, the universe will grow increasingly large and diffuse. Regions will drift apart until they become effectively isolated. If dark energy decreases, expansion might slow, but there's no evidence yet pointing in that direction. If dark energy changes in more complex ways, the future could follow patterns difficult to predict. These scenarios remain subjects of ongoing study. What has become clear is that the universe's geometry and its expansion are deeply connected. One cannot be fully understood without the other. The curvature affects the expansion path. The expansion influences how geometry is measured. Dark energy affects both. It acts as a bridge between geometry and evolution, shaping the trajectory of the universe without forming any structures itself. The flat geometry also influences how scientists calculate distances. In curved spaces, the relationship between distance and redshift changes. Light behaves differently over long paths. In a flat universe, these relationships become simpler, making certain measurements easier to interpret. This has practical benefits when studying distant supernovae, galaxy distributions, or gravitational lensing. It allows astronomers to compare large-scale observations more accurately. Even though the universe appears flat, this conclusion doesn't diminish the role of curvature on smaller scales. Space around massive objects still curves. Black holes bend space intensely. Stars and planets create measurable effects on light paths. These curvatures are local. The flatness applies only when averaging across enormous distances. Local curvature remains just as important for understanding the behaviour of objects within galaxies. One way to think about this distinction is to consider how the Earth's surface appears flat over short distances, but reveals curvature when viewed from far away. The universe behaves similarly but at massively larger scales. Locally, curvature appears. Globally, space behaves as though it has no overall curvature. The difference lies in scale, not in contradiction. Scientists also use the shape of the universe to test their models of inflation, a rapid expansion that occurred early in cosmic history. Inflation predicts that the universe should be extremely close to flat. The measurements of the cosmic microwave background support this. The agreement between theory and observation adds confidence to both inflationary models and the flat interpretation. However, slight deviations remain possible, and more precise measurements continue to refine these conclusions. As research continues, more data from galaxy surveys and cosmic background studies will help narrow the possibilities further. Space missions and ground-based observatories are collecting information that helps refine estimates of curvature. So far, the results hold steady. The universe behaves almost perfectly flat. The shape of the universe, however, doesn't settle the question of its ultimate fate. Geometry informs the possibilities, but dark energy determines the direction. The paths the universe can take remain tied to how dark energy behaves over time. If dark energy stays constant, expansion will continue accelerating. If it changes, the evolution could shift. These possibilities remain open, and scientists continue exploring them through increasingly detailed observations. Even though the shape might seem like a grand or distant concept, it plays a practical role in understanding everything from cosmic structure to the behaviour of light across billions of years. It defines the framework within which galaxies evolve. It determines how far we can see. It sets the stage for the universe's long-term direction, and the nearly flat geometry has become a central feature of how scientists model the cosmos. For most of the history of astronomy, the sky looked like a place where change was rare. Stars kept their positions, galaxies maintained their shapes, and even when astronomers began to record the motions of distant objects, the changes they saw were slow enough that they didn't challenge the idea of a universe unfolding gradually. The expansion discovered in the early 20th century brought a new level of dynamism into the picture, but even that expansion seemed steady. It wasn't until researchers started looking closely at certain exploding stars that the story changed. These explosions revealed that the universe wasn't expanding at a fixed pace, it was speeding up. And the evidence came from one of the few types of objects bright enough to mark distances across billions of light years. These objects are supernovae, specifically a type known for having a reliable brightness pattern. Their consistency made them invaluable tools. The idea behind using them was simple. If an object always reaches the same peak brightness when it explodes, then measuring how dim it appears from Earth tells you how far away it is. The farther the object, the dimmer it looks. Astronomers can compare the measured brightness to the expected brightness and calculate the distance with reasonable precision. In the broader structure of cosmic measurements, this method became one of the most trusted ways to reach deep into the universe. The type most often used for this purpose is known as type Ia. These explosions occur when a white dwarf star in a binary system gathers material from its companion until it reaches a critical mass. When this mass is exceeded, the star collapses inward and then detonates in a thermonuclear explosion. Because the conditions required for this event are very specific, the resulting brightness is extremely predictable, not identical in every case, but consistent enough to allow careful measurement. Astronomers began collecting data from these supernovae to see how the universe had changed over time. The idea wasn't to test whether acceleration existed. At first, they expected to confirm the slowing expansion predicted by gravity, since the universe contains matter and matter creates gravitational pull. The expansion should have been decreasing over billions of years. The aim of the measurements was simply to determine how much it had slowed. But as more distant supernovae were observed, a pattern emerged that didn't match expectations. The light from those distant explosions wasn't just dim, it was dimmer than the calculations predicted. The usual interpretation of a dimmer signal is that the object is farther away, but these supernovae shouldn't have been as far away as the data suggested. Something didn't fit. When astronomers examined the relationship between distance and redshift, the mismatch grew clearer. The only conclusion that explained the observations was that the expansion had been slower in the past and had increased over time. The galaxies that hosted these explosions had drifted farther away than earlier models predicted, because the expansion had accelerated since the light was emitted. Two research teams, working independently and using different sets of data, reached this conclusion. Both groups carefully reviewed their results, checked for errors, and tested alternative explanations. Dust, supernova variations, and measurement inaccuracies were all considered. But none of these factors could account for the uniform pattern. The dimness of the distant supernova was a direct sign of acceleration. The discovery didn't rely on a single observation. It emerged from the consistent behavior of dozens of explosions at various distances. The more supernovae astronomers measured, the clearer the pattern became. These explosions acted as markers scattered across cosmic time. Each one recorded the expansion rate at the moment its light began travelling through space. Together they formed a record stretching across billions of years, and that record showed a universe that had changed its pace. One reason supernovae are so effective for this purpose is that they combine brightness with distinct spectral features. These features shift in predictable ways as the universe expands. By measuring these shifts, astronomers determine the redshift. Redshift provides information about how much space has stretched since the supernova occurred. This, paired with the distance derived from brightness forms, the foundation for understanding the expansion rate at different times. If the expansion was slowing, the redshift distance relationship would follow a particular curve. If it were accelerating, it would follow a different one. The data followed the accelerating pattern. The recognition of acceleration introduced new questions. If the expansion was speeding up, what was driving it? The idea of dark energy emerged as a description of this unknown influence. It wasn't a direct detection, it was an explanation for the behavior revealed through the measurements. Dark energy became a placeholder for the cause of the acceleration, much like how early scientists used terms such as phlogiston before understanding combustion. The name described an effect without identifying the underlying mechanism. Supernova measurements continued to improve. Instruments became more sensitive. Telescopes gained better resolution. Surveys expanded to include more distant events. These improvements allowed astronomers to refine the expansion history with increasing accuracy. The pattern remained consistent. As the supernovae grew more distant, the evidence for acceleration became stronger. The conclusion wasn't based on a small sample. It came from sustained effort across many years and multiple independent studies. The cosmic microwave background later provided supporting evidence. Its patterns reflected the early universe's conditions, and those patterns were consistent with a model where dark energy dominates the present-day expansion. But supernovae remain the primary tool that revealed the acceleration in the first place. Their brightness, their predictable behavior, and their appearance across vast distances made them uniquely suited for uncovering the universe's changing expansion rate. One of the interesting aspects of using supernovae as cosmic markers is that they act as time capsules. The light from a supernova that occurred billions of years ago carries information about how the universe behaved at that time. The brightness tells us how far the light has travelled. The redshift tells us how much the universe has expanded during that journey. Together they form a snapshot of the universe's expansion at a particular moment. By studying supernovae from different periods, astronomers can piece together how the expansion has changed. These time capsules show a clear pattern. The oldest supernovae reveal a slower expansion. The more recent ones show a faster expansion. The change between these two eras reflects the growing influence of dark energy. When the universe was young, matter dominated. Gravity pulled inward strongly enough to slow the expansion. As the universe grew, matter became less dense. Meanwhile, dark energy remained constant in its density. Eventually, the influence of dark energy surpassed that of matter, shifting the expansion into an accelerating phase. The supernova data reflect this transition. This transition wasn't abrupt. It happened over billions of years, but the difference between the early expansion and the later expansion comes clear through careful measurement. The light curves of the supernovae, the precise timing of their brightness changes, and the details of their spectra all contribute to the accuracy of the measurements. Every data point adds to the pattern, and the consistency across many independent observations reinforces the conclusion. Even with this evidence, researchers continue to examine whether supernovae evolve over time. If their brightness varied in unexpected ways across billions of years, it could influence distance calculations. To test this, astronomers compare nearby supernovae to distant ones, searching for subtle differences. They analyze host galaxies. They examine environmental influences. So far, the basic behavior appears stable enough for the method to remain reliable. While minor adjustments have been made to refine the technique, the overall pattern of acceleration remains unchanged. Another layer of complexity involves understanding the distribution of dust and gas that could affect supernova brightness. Dust can dim light, but it usually does so in ways that leave identifiable signatures in the spectrum. By analysing these signatures, astronomers can correct for the dimming. These corrections help ensure that the measurements reflect the true distances. Again, the data remain consistent with cosmic acceleration, even after accounting for these factors. Supernova measurements also help test alternative models of the universe. Some theories attempt to explain the acceleration without invoking dark energy. They propose modifications to gravity or new types of interactions. By comparing the predictions of these models to the supernova data, scientists can rule out some possibilities and refine others. The continued agreement between observations and the dark energy-driven model reinforces the idea that dark energy plays a central role in cosmic evolution. In addition to their use in measuring cosmic expansion, supernovae have contributed to broader questions about the nature of the universe. Their distribution across different types of galaxies helps researchers understand star formation histories. Their frequency provides insight into the life cycle of certain stars. Their interaction with surrounding material reveals details about galactic environments. All of these pieces add to the larger picture of how matter evolves over cosmic time. But the most far-reaching contribution remains their role in revealing cosmic acceleration. Supernova surveys have expanded significantly in recent years. Projects using ground-based telescopes, space-based observatories, and automated search programs now detect thousands of supernovae. With such large samples, the statistical power of the measurements grows. Instead of relying on a few dozen explosions, researchers can analyze thousands. This improves confidence and reduces uncertainty. The greater the number of observations, the more clearly the acceleration stands out. The next generation of observatories aims to improve this picture even further. New telescopes with wider fields of view will scan the sky more frequently, capturing transient events with greater efficiency. Instruments designed specifically for studying dark energy will analyze thousands of supernovae across many epochs. These efforts aim not only to confirm the acceleration, but also to determine how dark energy behaves over time. If dark energy evolves, the supernova data might reveal subtle deviations. If it remains constant, the pattern will continue following current models. Even as instruments become more advanced, the fundamental method remains the same. Measure brightness, measure redshift, compare the results. This straightforward approach, combined with careful calibration, continues to offer some of the clearest evidence for the universe's accelerating expansion. The path from these measurements leads directly into broader questions. If the expansion accelerates, where does it lead? How does the balance between matter and dark energy change over time? Will dark energy continue to dominate, or could it shift? These questions remain open, but the insights gained from supernovae provide a foundation for exploring them. Without these exploding stars, the evidence for acceleration would be far weaker. They serve as markers that trace the universe's history, offering a way to see how the cosmos has changed across billions of years. The idea that the emptiest places in the universe are not truly empty can feel counterintuitive at first. People often imagine a vacuum as a silent, featureless region where nothing exists and nothing happens. It's natural to think of space that way, especially when daily life doesn't offer any examples of true emptiness. But when researchers began exploring matter, energy, and the forces of nature at the smallest scales, they found that the concept of a perfect void doesn't align with how the universe behaves. Instead, the closer they looked, the more activity they found hidden beneath what seems like quiet emptiness. This recognition emerged gradually as quantum theory developed. Early experiments focused on understanding atoms, electrons, and other small particles. As instruments improved and theories became more precise, scientists learned that particles don't behave like miniature objects moving through empty space. They behave more like excitations of fields that extend throughout the universe. In this view, particles are not isolated entities that appear and disappear on their own. They are local disturbances of fields that already exist everywhere. This shift in perspective changed how scientists think about space itself. If particles arise from fields, then the fields must exist even where no particles are present. A vacuum is not an absence of everything. It is a region where fields sit in their lowest energy state. Even in that state, the fields retain energy. They never settle into perfect stillness. Instead, quantum mechanics predicts that fields fluctuate constantly in subtle ways. These fluctuations are too small and too brief to observe directly, but their effects appear in experiments that probe the fundamental structure of matter. These fluctuating fields contribute energy to empty space, and that energy influences how the universe behaves on large scales. This energy is often called vacuum energy. It isn't energy in the familiar sense of heat, motion, or radiation. It doesn't make a region glow or warm up. Instead, it acts as a constant background energy present everywhere. It doesn't vary from one place to another, and it doesn't depend on whether matter is present. Its properties make it difficult to detect directly, but they also make it a strong candidate for explaining why the universe's expansion accelerates. The idea that vacuum energy might influence cosmic expansion emerged long before scientists discovered acceleration. Einstein introduced a term in his equations called the cosmological constant. At the time, he used it to maintain a static universe, since people believed the universe was unchanging on large scales. Later, after expansion was discovered, the term fell out of use. It was considered unnecessary. But the idea resurfaced when acceleration was measured. A cosmological constant behaves like a uniform energy density in empty space. It produces an outward push that becomes noticeable over cosmic distances. Vacuum energy fits this description closely. Quantum physics adds more nuance to the idea. According to quantum theory, the vacuum contains energy because fields cannot reach absolute zero. They always fluctuate. These fluctuations create temporary pairs of particles and antiparticles that appear and vanish quickly. These pairs don't persist long enough to become real particles, but they leave tiny effects that can be detected in certain experiments. The Casimir effect, for example, shows that two metal plates placed very close together experience a small force caused by changes in vacuum energy between them. The effect is subtle but measurable, supporting the idea that empty space is active in ways that classical physics cannot explain. However, when physicists attempt to calculate the total vacuum energy predicted by quantum theory, the results conflict with observations. The theoretical value is much higher, far larger than what the expansion rate of the universe allows. If the vacuum contained that much energy, the universe would expand far too quickly for stars or galaxies to form. The mismatch between theory and observation is not small, it is enormous. This discrepancy remains one of the biggest unresolved problems in modern physics. Despite this mismatch, vacuum energy remains one of the strongest explanations for dark energy. Observations show that empty space exerts a gentle but persistent influence on cosmic expansion. The simplest explanation is that space contains energy that does not dilute as the universe expands. Matter becomes less dense over time, radiation becomes less dense as well. But vacuum energy remains constant. As space grows, its total contribution increases. At some point, its influence overtakes that of matter and radiation, leading to accelerated expansion. This transition appears to have occurred billions of years after the Big Bang. In the early universe, matter dominated. Gravity slowed the expansion. But as matter spread out, its influence weakened. When vacuum energy began to outweigh matter on large scales, the expansion shifted into an accelerating phase. Supernova observations revealed that this shift had occurred, and additional measurements reinforced the conclusion. Something in empty space was driving the acceleration. Researchers continue exploring how quantum fluctuations contribute to this behavior. Some ideas suggest that vacuum energy may change slowly over time. Others propose that the influence we call dark energy might come from a field that adjusts gradually. These ideas fall under broader concepts like quintessence, but no direct evidence has yet confirmed them. The most straightforward explanation remains that vacuum energy behaves as a cosmological constant, maintaining a steady presence throughout space. Another way scientists study quantum fluctuations is by examining how they affect the forces of nature. Certain experiments reveal that vacuum fluctuations slightly alter the behavior of charged particles. This effect must be included in calculations to match experimental results. These subtle influences show that quantum fluctuations are real and measurable, even if they remain invisible in a direct sense. Their presence reinforces the idea that the vacuum has structure and energy. This structure becomes even more evident when considering interactions with gravity. Gravity responds to all forms of energy, even those that cannot be observed directly. Since vacuum energy fills space uniformly, it influences gravity on large scales. It does not pull objects together like ordinary matter. Instead, it acts as a kind of negative pressure that pushes outward. This behavior is consistent with the observed acceleration. It also fits the equations of general relativity when a cosmological constant is included. Together, these ideas create a unified picture. Quantum fluctuations fill space with energy, and that energy affects cosmic expansion. The relationship between vacuum energy and gravity is part of a broader challenge in physics. General relativity describes gravity at large scales, while quantum theory describes matter and energy at the smallest scales. Unifying these theories remains one of the biggest goals in theoretical physics. The mismatch between predicted and observed vacuum energy lies at the intersection of these two frameworks. Understanding it may require a new theory that connects the quantum world with the gravitational one. Some researchers propose that space-time itself might have a granular or discrete structure at extremely small scales. Others suggest that new symmetries or principles might cancel out most of the vacuum energy, leaving only a small amount. Still others explore the possibility that vacuum energy is influenced by aspects of the universe we cannot observe directly. These ideas remain speculative, but they offer potential paths to resolving the discrepancy. Even though the nature of vacuum energy remains uncertain, its effects are visible through cosmic expansion. The stretching of space affects the light from distant galaxies. It influences the growth of cosmic structures. It determines how the universe evolves over time. These effects provide indirect evidence for vacuum energy's presence. Instead of observing it directly, scientists detect its influence on the universe's behavior. One of the important features of vacuum energy is that it doesn't interfere with everyday activity. It doesn't push objects apart locally. It doesn't alter the structure of atoms. Its influence becomes noticeable only across vast distances where gravity becomes weak. This subtle behavior explains why dark energy wasn't discovered until researchers analyzed distant supernovae. The influence doesn't appear at human scales or even galactic scales. It appears only when considering the universe as a whole. This makes vacuum energy difficult to study directly. Researchers rely on indirect methods, such as examining how structures form and evolve, how light travels across the universe, and how the cosmic microwave background is shaped. These observations provide constraints on how much vacuum energy exists and how it behaves. They also help refine models of dark energy and cosmic expansion. As more data accumulate, the constraints become tighter. Another challenge is separating the effects of vacuum energy from those of matter and dark matter. While matter clumps, vacuum energy remains uniform. This distinction helps researchers distinguish between the two, but it also complicates models of structure formation. Simulations must include both influences to produce accurate predictions. These simulations have improved greatly in recent years, and they consistently support the idea that vacuum energy plays a major role in shaping the universe's large-scale behavior. Despite its subtle influence, vacuum energy has profound implications for the future. If its density remains constant, the expansion will continue accelerating. Over long periods, galaxies outside our local group may drift so far away that their light will no longer reach us. The observable universe will effectively shrink. Local structures will remain intact, held together by gravity, but anything beyond the reach of that gravitational binding will drift away. The universe will grow more diffuse and isolated over time. If vacuum energy changes, different scenarios become possible. A decrease could slow the expansion. An increase could accelerate it more strongly. Some models suggest that vacuum energy might fluctuate in ways that alter cosmic evolution. These scenarios remain speculative, but they illustrate how sensitive the universe's future is to the behavior of vacuum energy. Much of the ongoing research focuses on understanding whether vacuum energy truly remains constant. New observatories, surveys, and analyses aim to detect even small variations. If such variations exist, they could reveal new aspects of fundamental physics. If not, the cosmological constant remains the simplest description of dark energy. Whatever the outcome, vacuum energy remains one of the central concepts shaping our understanding of the universe. It connects quantum mechanics with cosmology. It brings together ideas about fields, fluctuations, and gravitational behavior. It influences the largest structures in existence without interacting directly with matter in familiar ways. This combination makes it both elusive and essential. When people first hear about ideas such as multiverses or hidden forces, they often assume they belong only to science fiction or imaginative speculation. It's easy to think that anything beyond the observable universe must be purely hypothetical. But in modern cosmology, these concepts emerge naturally from attempts to explain the discoveries that don't fit within older frameworks. They aren't introduced to create dramatic possibilities. They appear because the data lead to questions that require new approaches. These ideas may seem unusual at first, but they grow from the same scientific reasoning that helped reveal cosmic expansion, dark matter, and dark energy. The starting point for many of these discussions is the realization that the universe behaves differently at different scales. At the level of galaxies and clusters, gravity dominates. At the level of the cosmos, dark energy shapes the expansion. At very small scales, quantum mechanics governs matter and energy. Each layer of physics works well in its own domain, but connecting these layers into a single framework remains one of the biggest challenges in science. The possible existence of multiverses, new fields, or hidden forces arises from attempts to address these gaps. One of the earliest ideas related to the multiverse comes from inflation, the rapid expansion that occurred in the universe's earliest moments. Inflation was proposed to explain why the universe appears so uniform on large scales, and why its geometry seems nearly flat. The theory predicts that during this early period, space expanded exponentially, smoothing out irregularities. This rapid expansion helps explain many features of the universe, including the distribution of galaxies and the patterns in the cosmic microwave background. Inflation has become a central part of modern cosmology because it matches observation so well. However, inflation doesn't necessarily stop everywhere at the same time. In some models, inflation ends in certain regions while continuing in others. The regions where it ends become pockets of space where matter forms, stars ignite, and galaxies develop. The regions where it continues expand faster than anything inside them can keep up. This leads to a picture where different regions of space might experience different conditions. Each region becomes a universe with its own characteristics, separated from others by enormous stretches of inflated space. This scenario is called eternal inflation. It isn't part of everyday experience, but it comes directly from the mathematics of inflationary models. In this framework, the multiverse isn't introduced as a wild idea. It's a natural outcome of how inflation behaves. Researchers studying the early universe consider these possibilities because they arise from the equations, not because they seek to add complexity, even though there is no way to observe these other regions directly. The idea remains part of the broader effort to understand how the universe began and why it has its current properties. Another approach to multiverses comes from theories involving extra dimensions. Some models of particle physics and gravity propose that the universe contains more dimensions than the familiar three of space and one of time. These extra dimensions could be tightly curled or extended in ways we cannot observe directly. In some theories, different regions of space might have different arrangements of these dimensions. If the structure of extra dimensions varies, the physical laws might vary as well. This leads to another form of multiverse where different regions exhibit different physical properties. Again, This idea stems from attempts to unify the forces of nature rather than from speculation for its own sake. These multiverse ideas remain unconfirmed because they involve regions beyond our observational reach. But even though they can't be tested directly, they serve as helpful frameworks for thinking about unresolved problems. They allow scientists to explore how different conditions could lead to universes with varying properties, and whether our universe's characteristics are inevitable or simply one possibility among many. Beyond the idea of multiple universes, researchers also investigate new fields that might exist throughout space. These fields could help explain dark energy, dark matter, or other unexplained phenomena. For example, some theories propose a slowly varying field that influences the expansion of the universe. Unlike vacuum energy, which remains constant, such a field could evolve over time. If it changes gradually, it might produce an effect similar to dark energy, but with different long-term behavior. These fields are known as scalar fields. They appear in many theoretical models because they offer flexible ways to describe unknown influences. Scalar fields could also relate to dark matter. While dark matter acts through gravity and does not interact with light, some theories propose that dark matter might arise from a new type of field that creates particles in a way that differs from ordinary matter. These models remain under investigation because they could explain why dark matter hasn't been detected directly despite its significant gravitational influence. Hidden forces are another possibility. Our understanding of the universe relies on 4 fundamental interactions: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. These forces explain most of the behavior observed in nature. But some theoretical models suggest that additional forces might exist. These forces would have limited effects at familiar scales, but could influence cosmic expansion or the behavior of dark matter. If such forces exist, they might operate through particles that interact very weakly with ordinary matter, making them difficult to detect. One motivation for exploring hidden forces is the challenge of unifying gravity with quantum mechanics. Gravity behaves smoothly on large scales, as described by general relativity. Quantum theory describes particles with energy levels, uncertainties, and fluctuations on small scales. Combining these frameworks has proven difficult. Some models that attempt this unification introduce new interactions that emerge only under specific conditions. These interactions might influence vacuum energy, cosmic expansion, or the early universe's behavior. While these possibilities remain speculative, they help guide research into areas where new discoveries might emerge. Another motivation comes from attempts to understand the apparent fine-tuning of the universe. Many physical constants, such as the strength of gravity or the properties of particles, appear to have values that allow for stable matter, stars, and galaxies. If these constants were slightly different, the universe could look very different. Some researchers explore whether hidden forces or extra fields might play a role in setting these constants. Others consider the multiverse as a possible explanation, where different regions might exhibit different parameters, and only certain regions can support complex structures. These ideas are not used to avoid difficult questions. They emerge from the effort to find coherent explanations that align with observations and with the laws of physics. When the current frameworks leave gaps, new possibilities arise. They may or may not prove correct, but they help map the space of potential explanations. The concept of additional fields also appears in attempts to describe inflation more precisely. The early universe likely involved extremely high energies, where familiar forces behave differently. Scalar fields may have driven inflation, shaping the universe's initial conditions. These fields might leave subtle traces in the cosmic microwave background, or in the distribution of galaxies. Researchers look for these traces through detailed observations, comparing data with theoretical predictions. While no definitive signatures have emerged yet, the analysis continues, guided by both theory and observation. Even though these exotic possibilities might seem distant from everyday experience, They remain grounded in mathematical frameworks and observational constraints. Scientists don't adopt new ideas lightly. Each possibility must explain current data and predict outcomes that can be tested in the future. As more measurements accumulate, theories become refined. Some ideas strengthen while others fall away. This gradual process shapes the direction of research. The search for hidden forces often overlaps with the search for dark matter. Many experiments look for interactions that might reveal dark matter particles. Underground detectors attempt to catch rare collisions. Particle accelerators search for new particles. Space-based observatories measure cosmic rays and gamma rays. While no definitive detection has been made, the range of possibilities continues to narrow. Each constraint helps refine which models remain viable. Similarly, the search for fields related to dark energy involves precise measurements of cosmic expansion. Surveys of galaxies, supernovae, and gravitational lensing aim to detect whether dark energy changes with time. If it does, the pattern of acceleration will shift subtly. If it does not, the simplest interpretation, a cosmological constant, remains consistent. These observations guide the development of models, helping determine whether new fields are needed. The multiverse ideas, while not directly testable, still shape how scientists think about cosmology. They provide context for understanding why the universe has certain properties. They also influence discussions about the limits of observable science. While researchers cannot detect other universes, they can explore the implications of such models for the part we can observe. For example, some versions of inflation predict specific patterns in the cosmic microwave background. If such patterns were discovered, they could support the idea that inflation behaves in ways that naturally lead to a multiverse. The interplay between these exotic possibilities and observable science highlights an important aspect of cosmology. Even the most speculative ideas must connect to measurable phenomena. Models that introduce new fields must show how those fields influence the cosmic expansion. Theories involving hidden forces must explain how those forces affect matter or energy. And multiverse models must demonstrate how the early universe behaves in ways consistent with observations. Without such connections, theoretical ideas do not gain traction. This approach ensures that speculation remains anchored to evidence. Even when ideas extend beyond direct observation, they must remain grounded in physics. The same process that revealed cosmic acceleration guides the exploration of these new ideas. Careful measurement, repeated observations, and rigorous testing shape which possibilities survive. This discipline makes scientific inquiry robust, even when exploring realms far beyond ordinary experience. As researchers continue exploring these possibilities, they keep returning to the central question: why does the universe behave the way it does? Why does expansion accelerate? Why does matter cluster in certain ways? Why do physical laws have their particular forms? Exotic ideas emerge not to create complexity, but to fill gaps where existing theories fall short. They provide ways to explore deeper structures that may one day become part of established science. The next steps in this exploration depend on new observations. Upcoming telescopes will map galaxies more precisely. Experiments will probe particle interactions at higher energies. Cosmic microwave background studies will search for patterns that might hint at new physics. Each new piece of data will help refine these possibilities, moving some ideas closer to acceptance while ruling out others. These efforts build naturally on the ideas discussed earlier: the role of dark energy, the behavior of empty space, and the influence of cosmic expansion. The exploration of exotic possibilities is part of the larger effort to understand what drives the universe and how its deepest structures operate. Even though many questions remain open, the direction of inquiry remains steady, guided by evidence, theory, and a desire to understand the universe at every level. Thinking about the distant future of the universe often starts with a simple question: what happens when expansion continues without stopping? The galaxies today are already drifting apart at increasing speeds, and dark energy has taken over as the dominant influence on cosmic behaviour. But the effects of this acceleration unfold over timescales that stretch far beyond anything familiar. Understanding what lies ahead requires stepping away from the usual sense of time and imagining a universe where the changes are slow, steady, and shaped by forces that operate quietly across vast distances. The expansion we observe today didn't begin in its current form. In the early universe, matter was packed tightly. Gravity pulled strongly, shaping the first stars and galaxies. Over time, as space grew and matter became more diffuse, the influence of dark energy increased. It didn't suddenly appear. Its presence simply became more significant as matter spread out. Now its effect dominates the universe's large-scale behaviour. That dominance is expected to continue, influencing the evolution of everything from galaxy clusters to the great empty stretches between them. As the expansion accelerates, the distances between galaxies grow more quickly. The galaxies themselves remain intact because their internal gravity is strong enough to resist the expansion. But the space between galaxy clusters stretches at a pace that outstrips their ability to remain connected. Over long periods, these clusters drift farther apart. The expansion becomes more noticeable not as a force acting on the galaxies, but as a geometric transformation of space. This distinction is important for understanding what the future holds, because it explains why certain structures persist while others drift away. Over the next several billion years, the galaxies within the local group, which includes the Milky Way, Andromeda, and several smaller galaxies, will continue interacting. The Milky Way and Andromeda are expected to merge in the distant future, forming a single large galaxy. Gravity guides these interactions. Even though the universe's expansion accelerates, it does not overcome the gravitational connection within the local group. These interactions unfold slowly, with stars following long trajectories influenced by the combined gravitational pull of both galaxies. Outside the local group, however, other galaxies will drift farther away. Over time, the acceleration will create a kind of isolation. Regions of space that are gravitationally bound will remain intact, but everything beyond those boundaries will move beyond reach. Light from distant galaxies will stretch to longer wavelengths as space expands, making those galaxies appear fainter. Eventually, their light will shift so much that it will no longer be detectable. The night sky, at least on cosmic timescales, will grow less populated. This gradual process doesn't affect stars within galaxies. Their life cycles continue, shaped by internal processes rather than cosmic expansion. Fusion inside stars continues, elements form, and energy flows outward. But even these processes operate on long timescales. Large stars burn through their fuel relatively quickly, ending in supernova explosions or collapsing into black holes or neutron stars. Smaller stars burn more slowly and can last for trillions of years. These long-lived stars dominate the distant future because their stable fusion continues long after the larger stars have vanished. As stars age and exhaust their fuel, galaxies gradually grow dimmer. Star formation slows when gas clouds become depleted or heated. The galaxies become populated mainly by old stars, remnants, and faint, long-lived red dwarfs. At this stage, galaxies remain recognizable structures, but their brightness declines. This change doesn't affect their shape or internal behavior significantly, but it alters the distribution of energy within them. The acceleration of the universe continues during this time, but its influence remains primarily on the larger scales. The galaxies don't expand with the universe. They stay bound by gravity, but the space between galaxy clusters stretches faster, increasing the separation. Over long enough periods, this trend creates regions of the universe that are effectively isolated from one another. Communication between these regions becomes impossible using light or any form of signal, because the signals cannot outpace the expansion. This isolation influences how scientists think about the far future. It suggests that the universe will become a collection of island-like regions, each containing a few gravitationally bound galaxies. Outside these regions, the universe becomes increasingly empty. The vast distances created by the accelerating expansion make travel between regions impossible, even in principle. Light cannot bridge the growing gaps. The expansion outruns any attempt to connect distant regions. The far future is not defined by dramatic events. Instead, it unfolds through gradual changes that accumulate over unimaginable spans of time. As star formation slows, the distribution of matter becomes dominated by remnants. White dwarfs, neutron stars, and black holes become more common. Over even longer timescales, white dwarfs cool and fade. Their glow dims gradually until they become cold, faint objects. This cooling takes longer than the current age of the universe, so it occurs far into the future. The role of black holes becomes more prominent in this distant era. They remain as some of the most massive and stable remnants of earlier cosmic processes. While they do not dominate the universe in number, their presence becomes increasingly important as other objects fade. Black holes slowly lose mass through a process known as Hawking radiation, a theoretical prediction suggesting that black holes emit energy over extremely long periods. This process is incredibly slow for large black holes, but over vast timescales, it becomes significant. Eventually, even massive black holes will lose enough mass to evaporate entirely. This evaporation unfolds gradually, with the final stages occurring quickly after a long period of slow change. Throughout this time, the accelerated expansion continues. The scale of the universe grows beyond anything measurable. Regions that were once connected become separated by distances too great for any interaction. The influence of dark energy remains constant unless it evolves in ways not yet understood. If dark energy remains steady, the expansion continues indefinitely, shaping the far future into a universe where space grows more and more empty. Some theoretical models consider the possibility that dark energy might change. If it becomes stronger with time, the expansion could accelerate even more dramatically. In extreme versions of this scenario, the expansion could become so strong that it overcomes gravitational binding even within galaxies. Structures once thought immune to expansion might eventually break apart. This scenario is not supported by current evidence, but it remains a theoretical possibility. Other models suggest that dark energy might diminish over time, slowing the expansion. If this occurred, the universe might follow a different trajectory. However, no current observations point towards such a shift. Another aspect of the far future involves the gradual cooling of the universe. As space expands, the cosmic microwave background becomes stretched to longer wavelengths. It cools toward absolute zero. Energies become more diluted. As galaxies fade and radiation spreads out, the universe continues toward a state where temperatures approach a uniform, extremely cold value. This process does not create a simple or final state, but reflects the ongoing effects of expansion. Even in this distant cold future, activity continues. Particles interact rarely but not never. Quantum effects persist. Gravity continues shaping what remains. Black holes slowly evaporate. The processes operate on timescales far beyond anything encountered in day-to-day life, but they remain part of the universe's behavior. The future is not static. It is simply slow. Some theories explore even farther possibilities. They consider whether particles remain stable indefinitely, or whether new interactions might become important at extreme times. These ideas extend beyond current evidence, but they offer ways to explore how the universe's fundamental structure might evolve over long periods. The behavior of dark energy, the decay of particles, and the influence of quantum fluctuations could all shape the far future in ways that current observations cannot entirely predict. In each scenario, the expansion of the universe remains central. Whether it accelerates steadily, changes gradually, or evolves in unexpected ways, the expansion shapes the cosmic future. It determines how structures remain connected or drift apart. It influences how energy spreads. It affects the long-term behavior of matter, radiation, and space itself. As the universe continues expanding, the separation between regions increases. Galaxy clusters that remain gravitationally bound will continue existing as isolated structures. Within them, stars orbit the centers of their galaxies. Remnants move slowly through space. Gravity keeps the local environment stable, while the universe around it stretches. Over time, these clusters remain as the last connected structures in a universe that grows increasingly empty. Beyond these clusters, space expands without limit. Distances grow faster than any signal can traverse them. The horizon, beyond which no information can reach, shrinks in practical terms. Even though the universe itself might remain infinite, the observable regions become smaller from any given point. This effect doesn't signal an ending. It simply shapes how the universe evolves. The story of the far future of the universe is not about a single event. It's about processes that unfold gradually and steadily. Expansion increases. Stars age. Clusters drift apart, remnants cool, black holes evaporate. Each of these processes contributes to the long-term evolution of the cosmos. None of them represent a final point. They simply reflect how the universe behaves under the influence of dark energy and cosmic expansion. When people talk about the expansion of the universe, the idea can feel distant from everyday life. Nothing around us stretches. Distances between familiar objects stay the same. Gravity holds the Earth in its orbit. Buildings don't slowly drift apart. Even the solar system behaves predictably. Because expansion is so subtle at human scales, it's easy to imagine it as something happening far away, affecting only distant galaxies or regions of space we'll never reach. But the expansion plays a quiet, steady role in shaping where we fit within the universe. Even though we don't notice it directly, it determines how the cosmos evolves and how our position relates to everything around us. The expansion started in the early universe, long before stars or galaxies formed. That early period set the foundation for the structures that came later. If expansion had been faster, matter might have spread out too quickly for galaxies to form. If it had been slower, gravity might have collapsed matter into dense regions before stars had time to ignite. The rate of expansion shaped everything we see today. Our location within the Milky Way, the presence of nearby galaxies, and the structure of the local group all depend on how the universe expanded in its earliest phases. As matter cooled and clumped under gravity, galaxies formed. These galaxies became the building blocks of larger structures. But even as galaxies grew, the expansion continued, slowly increasing the distances between them. This balance between gravity and expansion determined how groups and clusters formed. If expansion had been significantly different, the Milky Way and Andromeda might not have become neighbours. Their eventual merger would not be part of the cosmic story. Instead, they might have drifted in unrelated paths, or formed in regions where their interactions would never occur. The local group's existence depends on this balance. It is a small collection of galaxies held together by their mutual gravitational pull. Despite the accelerated expansion of the universe, the forces within the group remain strong enough to prevent its members from drifting apart. This region forms our immediate cosmic environment. Its size, shape, and behavior all reflect the universe's history of expansion. Looking beyond the local group, the effect of expansion becomes more pronounced. The galaxies that are not bound gravitationally to us drift away over time. Their increasing distance affects what we can observe. As the expansion accelerates, the light from these galaxies becomes stretched to longer wavelengths. Eventually, it might become too faint or too shifted to detect. This gradual fading doesn't occur suddenly. It unfolds over long periods. But it influences what future observers will see when they look outward. This fading of distant galaxies shapes our understanding of cosmic history. By observing how the light from these galaxies is stretched, astronomers can measure the expansion. This measurement allows them to trace the universe's behavior across time. It helps determine how much dark energy influences the expansion and how the universe's rate of growth changes. Without these distant galaxies, our understanding of cosmic evolution would be far more limited. The expansion not only shapes our place, but provides the information needed to understand that placement. Even within the Milky Way, expansion contributes indirectly to our cosmic environment. The galaxy's size, shape, and structure depend on the conditions present when it formed. The distribution of matter in the early universe influenced where and how galaxies emerged. These conditions were shaped by expansion. The balance between the pull of gravity and the stretching of space determined how matter could collapse and organize into stars, clusters, and galactic disks. Our solar system formed within this structure, guided by patterns that were shaped long before planets existed. Understanding how expansion shapes our place also requires looking at how galaxies evolve. Over time, star formation changes. Gas clouds collapse, new stars ignite, and older stars fade. These processes occur independently of expansion, but the expansion influences the larger framework. Galaxies interact with neighbours, merge, and affect each other's structure. The accelerating expansion limits these interactions by separating galaxies over long distances. Only in regions where gravity overcomes the expansion do mergers occur. These interactions define the long-term evolution of galaxies, including the Milky Way. Within the local group, the future includes a merger between the Milky Way and Andromeda. This event is shaped by the balance of forces. While space expands, gravity still pulls the two galaxies together. Their eventual merger reflects how local conditions can override the general expansion. This merger will shape the future structure of the combined galaxy. It will influence the orbits of stars, the distribution of gas, and the gravitational environment in which future stars and planets form. Our place in the cosmos is not fixed. It changes gradually as galaxies interact, evolve, and follow the larger patterns of cosmic behavior. Looking farther out, clusters and superclusters offer another perspective. These larger structures are bound by gravity, but they exist in an expanding universe. Their shape and stability depend on the distribution of matter and the influence of dark energy. As expansion accelerates, the boundaries of these structures become clearer. Regions with enough mass remain connected. Regions without sufficient mass drift apart. This separation shapes the large-scale map of the universe. From our vantage point, the expansion determines what part of the universe is accessible. It sets the limits of what we can see and influences what information reaches us. Light from certain distant regions may never arrive if the expansion outpaces it. This limit defines the observable universe. Beyond it, space continues, but its details remain out of reach. The size of the observable universe changes over time as expansion stretches distances. This boundary is fundamental to understanding our place. It defines the part of the universe with which we can interact through light or any other signal. Another aspect of our place in the cosmos involves the balance of matter, radiation, and dark energy. Matter, which includes everything from stars to dust, influences the formation of structures. Radiation, including light and cosmic background signals, provides information about earlier periods. Dark energy drives the acceleration. Each of these components affects the universe in different ways. Their relative contributions shape the expansion's history. The current dominance of dark energy influences how rapidly regions drift apart. This balance determines the large-scale dynamics that define our cosmic neighborhood. Understanding this balance helps explain why we observe the universe in its current state. If matter dominated strongly, expansion would slow. If radiation dominated, the universe would behave differently. The particular balance we observe results from billions of years of expansion. This specific arrangement shapes how galaxies move, how clusters form, and where gravitational boundaries lie. Our position within the local group reflects how these influences interacted over time. Another part of the story involves the way expansion shapes the future. The accelerating expansion means that regions not bound by gravity will drift apart faster. Eventually, only local structures will remain within reach. Over immense timescales, the universe will become more isolated. This isolation is not immediate, it unfolds slowly. But it shapes the long-term environment in which galaxies exist. It determines how much of the universe remains accessible to future observers. It also affects how scientists interpret the large-scale structure of the cosmos. While expansion influences the large scale, it doesn't alter the solar system or the structure of atoms. Gravity and other forces dominate those scales. The distances between planets remain stable because gravity holds them in orbit. The structure of atoms remains unchanged because expansion affects only the geometry of space on extremely large scales. This difference helps explain why expansion is not noticeable in everyday experience. It shapes the universe without affecting small-scale structures. Even though expansion does not disrupt local systems, its influence remains central to understanding our place in the cosmos. It determines how galaxies are arranged, how clusters form, and how the observable universe evolves. It affects how information from distant regions reaches us. It shapes the long-term trajectory of cosmic evolution. Our position is not simply a location in space. It is a consequence of processes that span the entire history of the universe. The way expansion shapes our place becomes even clearer when considering how astronomers measure distance. Redshift provides a way to track how much the universe has expanded since light left a distant galaxy. This measurement allows scientists to determine where objects lie in relation to us. Without expansion, these measurements would be very different. The structure of the universe would not produce the same patterns. Our understanding of distance, time, and motion depends on the expansion. This approach helps place the Milky Way in the broader cosmic map. By measuring the redshift of nearby and distant galaxies, astronomers can trace the structure of the local group and its surroundings. They can determine which galaxies are bound to us and which are moving away. They can identify clusters and filaments, the large-scale structures that form the cosmic web. All of these depend on how expansion has shaped space. The cosmic web reflects the balance between gravity and expansion. Gravity pulls matter into strands and clusters. Expansion stretches the distances between these structures. The resulting pattern reveals how the universe evolved from a nearly uniform state to a rich structure filled with galaxies. Our place within this web reflects the history of both forces. We occupy a region where matter gathered enough to form stars and planets, yet not so dense as to collapse completely. This delicate balance places us within one part of a vast structure that extends across billions of light years. Understanding how expansion shapes our place also helps explain what we can learn from the cosmic microwave background. This ancient radiation carries information about the universe's early conditions. Its temperature variations reflect the seeds of future structures. These variations show how matter was distributed before galaxies formed. The expansion stretched this radiation over time, cooling it and changing its wavelength. By studying it, scientists can understand how the early universe set the conditions for the structures we observe today. This provides another perspective on how expansion influences our place. As expansion continues into the future, it will keep shaping the environment. The distances between clusters will grow. The observable universe will change. The local group will evolve through mergers and internal processes. These changes reflect larger trends rather than abrupt events. The expansion doesn't create sudden transformations. It shapes the cosmos gradually. The role of dark energy remains central in this process. Its influence determines how quickly expansion accelerates. If dark energy stays constant, the universe continues expanding at an accelerating rate. If it changes, the trajectory shifts. These possibilities affect the long-term distribution of matter. They influence how isolated regions become. They determine what future observers might see when they look outward. In each case, the expansion provides a backdrop that shapes the universe's behavior. It determines which structures remain connected, which drift apart, and how information travels across space. It defines the scale of the observable universe. It influences how matter collapses into stars and galaxies. Our place in the cosmos reflects the combined influence of these factors. The expansion continues to serve as a framework for understanding why the universe looks the way it does. It shapes both the near and the distant. It influences the past, present, and future, and it connects our location to the broader structure of the universe, allowing the larger picture to unfold at the same calm, steady pace seen throughout the cosmic story. It can be surprising how far a simple question about why galaxies drift apart leads. What began as a way to measure distances and study starlight has grown into a picture of a universe that expands steadily, guided by influences that act across immense scales. This widening of space doesn't announce itself. It has no sound, no motion you can feel, no effect on the objects around you. Yet it shapes the entire cosmic landscape. It guides the paths of galaxies, defines the limits of what can be seen, and sets the conditions for how the universe evolves. Even though the expansion feels remote, the wonder it carries comes from realizing that every part of the universe participates in it, including the region we call home. Thinking about this ever-widening universe leads naturally to a different kind of reflection, one that isn't centered on dramatic events, but on the quiet ways cosmic processes unfold. Instead of focusing on collisions or explosions, it brings attention to the steady progression of space stretching over billions of years. It encourages a slower pace, one that matches the nature of cosmic expansion itself. The universe's widening doesn't happen in bursts. It progresses steadily, allowing structures to evolve at their own pace. This gentle unfolding becomes easier to understand when examining how expansion influences everything from the earliest moments to the distant future. What makes this expansion feel so subtle is that its effects are invisible at familiar scales. The distances between atoms do not change because electromagnetic forces hold them tightly. The size of planets stays stable because gravity binds them. Even solar systems remain unaffected. Expansion matters only when the distances involved are vast enough that no other force dominates. This distinction becomes a useful way to see where expansion takes hold and where it remains absent. It's not an influence that pushes things apart. It's a geometric change that gradually alters the spacing between unbound objects. This geometric nature is one of the reasons the universe can expand without disrupting structures. Galaxies, bound by their internal gravity, stay intact. Their stars follow orbits. Gas clouds collapse into new stars. These processes rely on forces far stronger than the expansion's gentle effect. Yet the distances between galaxies grow because those galaxies are not bound to one another. Over cosmic timescales, this slow widening adds up, shaping a universe where clusters drift apart and the visible cosmos stretches into an increasingly distant view. Understanding this helps explain why the expansion rate tells us so much about the universe. When researchers discovered the acceleration, it changed every expectation about how the future might unfold. Instead of slowing under gravity, the expansion sped up. This shift didn't change daily life, but it changed how scientists interpreted the cosmic landscape. The acceleration implied the presence of an influence that does not diminish as space grows. Dark energy became the simplest way to describe it. Even though its nature remains unclear, its effects can be measured through redshift, supernova brightness, and the distribution of galaxies. The widening universe also changes how information travels. Light from distant galaxies stretches as space expands, shifting to longer wavelengths. This shift reveals how much the universe has expanded during the light's journey. It also determines whether the light will ever reach us. As acceleration continues, some regions drift away so quickly that their light will no longer cross the widening distance. This doesn't involve any boundaries or barriers, it's simply a consequence of expanding geometry. Over time, more regions slip beyond reach, leaving only the closest structures visible. This gradual change creates a sense of isolation on the larger scales, even though nothing dramatic happens in any moment. The galaxies in the local group continue interacting normally, unaffected by expansion, but the galaxies outside this region drift away steadily. Their presence in the night sky becomes increasingly faint, then imperceptible. This change occurs over such long time scales that it's more a shift in cosmic perspective than a loss of anything tangible. It reflects how expansion shapes what can be observed from any given point in the universe. These ideas often raise questions about the ultimate trajectory of cosmic evolution. If the universe widens indefinitely, does it reach a point where nothing else occurs? The answer depends on which timescales you consider. On human timescales, nothing changes. On cosmic timescales, the widening becomes more noticeable. Galaxies evolve, clusters drift apart, radiation stretches into longer wavelengths. The universe becomes more diffuse. But even in these fast stages, activity continues. Stars form from leftover gas. Black holes evaporate slowly. Particles interact occasionally. The universe does not reach an abrupt stopping point. It simply continues evolving at a pace that reflects the steady influence of expansion. What people often find surprising is how much of the universe's structure results from the exact balance of influences present in its early years. Expansion and gravity interacted in ways that allowed galaxies to form, but prevented matter from collapsing completely. If the early expansion had been different, the universe might have been empty or excessively dense. Instead, the balance allowed complexity to emerge. This balance shaped the environment that eventually supported stars, planets, and the conditions for life. It created the cosmic landscape in which humans now observe the universe's widening. This connection between early conditions and present behavior is one of the reasons cosmologists study both the distant past and the accelerating present. Each reveals different aspects of the universe's overall story. The early universe shows how matter began forming structures. The accelerating present shows how dark energy influences those structures as the expansion continues. Both periods shape what comes later. They reflect a long history guided by a combination of matter, radiation, gravity, and dark energy. As the widening continues, the large-scale patterns become more pronounced. Filaments stretch, voids expand. Clusters maintain their internal stability while drifting apart. The cosmic web remains structurally similar, but becomes less connected over time. This expanding web creates a map of how matter is distributed across the universe. It also provides a way to trace how expansion influences the arrangement of galaxies. The way expansion shapes this structure becomes clearer when considering how astronomers measure it. Observations of redshift provide a record of how the universe widened across time. Measurements from the cosmic microwave background reveal conditions from early moments. These data sets connect directly to the expansion rate. They show how the widening progressed and how the acceleration developed. Together, they offer a picture of a universe in continuous motion, guided by forces acting over immense distances. One of the most important aspects of the ever-widening universe is that it provides context for understanding our place within it. Even though humans occupy a small region of one galaxy, the larger cosmic setting explains why that region exists at all. The expansion allowed matter to cool and clump. Gravity shaped these clumps into stars and planets. The balance between expansion and gravity determined how galaxies formed and how they evolved. Without this balance, the environment that supports life would never have emerged. This connection is subtle but fundamental. Thinking about the widening universe also encourages questions about what future observers might see. As expansion continues, the light from distant galaxies will become more stretched. Some galaxies will eventually disappear from view entirely. Future astronomers may observe only the galaxies bound to their region, unaware of the wider structures that once filled the sky. Their view of the universe would be more limited, shaped by the expansion's progression. This raises interesting possibilities about how cosmic knowledge depends on when one exists in the universe's timeline. Even though the widening suggests isolation in the long run, it does not imply a diminishing of the universe's complexity. The structures within gravitationally bound regions remain active. Stars orbit their galactic centers. Gas clouds collapse into new stars. Remnants interact. Black holes merge. These processes continue even as the spaces between clusters grow. The universe becomes quieter in terms of intercluster interactions, but remains dynamic within local environments. The widening also affects how scientists interpret long-term cosmic evolution. The accelerating expansion changes how energy is distributed. Matter becomes less influential on cosmic scales. Radiation becomes increasingly stretched and faint. Dark energy becomes the dominant component. These shifts determine the long-term dynamics of space. They also influence how scientists think about theoretical models involving vacuum energy, fields, or new forms of matter. Each model offers a different explanation for the widening. Some rely on a constant energy associated with empty space. Others propose fields that evolve slowly. Some suggest modifications to gravity. Each possibility implies a different long-term trajectory for the universe. Observations continue to refine which models remain plausible. As measurements become more precise, scientists narrow down the possibilities. The widening universe becomes a backdrop against which these models are tested. As the universe continues to expand, the sense of wonder it inspires comes not just from its scale, but from its calmness. The widening doesn't disrupt. It doesn't create sudden changes. It simply continues, shaping the cosmos in a steady way. This quiet progression is one of the more surprising aspects of cosmic behavior. It shows how large-scale processes can be significant without being dramatic. It also reflects how the universe can evolve gently, even as its size increases without limit. This calmness becomes even more apparent when imagining the universe at times far beyond the present. The galaxies within local regions remain the centers of activity. Stars continue forming slowly. Remnants drift. Black holes evaporate. Expansion carries everything else farther away, widening the spaces between clusters. Yet no boundary is reached. The universe doesn't stop expanding. It simply continues, gradually reshaping the cosmic landscape. This ongoing widening encourages a particular perspective when considering the universe. Instead of looking for a clear ending or a final state, it becomes easier to see the universe as something that evolves continuously. Its behavior reflects the interplay of forces that act quietly but persistently. Each stage opens into another. The expansion doesn't lead to a conclusion but to a different arrangement. It creates a sense of openness rather than finality. Thinking about the ever-widening universe also highlights the idea that the cosmos doesn't need to have a final destination to be meaningful. Its steady stretching creates space for new structures to evolve, for stars to form, for galaxies to interact, and for the large-scale web to shift gradually. The widening becomes a backdrop for ongoing activity rather than a pathway toward a specific outcome. As the ideas developed in earlier sections continue into this final movement, the expanding universe becomes a way to connect everything together. The earliest fluctuations that seeded galaxies, the gentle competition between gravity and expansion, the rise of dark energy, and the long-term evolution of cosmic structures all point toward a universe that unfolds smoothly, shaped by steady influences. Each new piece fits into the larger picture, allowing the understanding to grow without urgency. And as this picture continues taking shape, the widening universe remains a steady presence, guiding the structure of the cosmos while leaving space for whatever comes next, carrying the story forward at the same quiet pace that has defined it since the beginning.